extinguishers that have taken place. Okay, this is a safe area where I have to evacuate. You know, if there is any incidence, there is an alarm, I'll be going out and converging on a safe area somewhere. And then if a safe area is stipulated, is the safe area being stipulated right, or is it next, so Shovanji, next to the gas storage areas, okay, or is it next to the utilities? You need to actually evaluate those little details to make sure you are building an absolutely safe workplace out for your entity. So if I actually take a look at it, it's a broad topic. You can keep on improving on it. I've already introduced myself to some of you. I am the chair for the Semiconductor Manufacturing Skill Committee at Electronics Sector Skill Council. I'm a professor at a state university in Haryana called Manav Rashna International Institute of Research Studies. I'm a retired applied materials person. I have a few other hats, those of you who know me. I do a lot of things relating to the industry post-retirement, and I enjoy every one of them. My firm history had been, what is it that we are missing out? And I emphasized it again and again that what we are missing out are manufacturing skills, which are absolutely different from design skills. You need design skills, you need manufacturing skills. So many times when we say we are going to skill people on semiconductors, it ends up going back into the manufacturing skills only. So we need to be very careful of what we are training people so that they can actually go and work on shop floors. This is what Sharath here, who's from CeNSE, has been driving in the manufacturing skills committee at for the semiconductor packaging workforce. This is what a whole range of thought leaders have been contributing to over the last couple of years to create the new courses and the curriculums and the qualification packs that have been fed into the programs now. Varun there, sitting silently, you should stand up and take a bow, is from the Electronic Sector Skill Council, the Standards Committee. Whatever recommendations the committee makes, he's the one who packages it, gets it through the NCVET and the Ministry of Skill Development and Environments, gets it out as a national occupation standards. Okay, so it's actually the effort of a lot of people to get these notes out to you. And I think our key objective is you should get a good taste of it so that you can take it out to the actual practice in the institutes and then actual practice in the industry. I will try and share some of those curriculums with you separately also as a course as a part of this. But the key message is India needs a lot of these, and these are not designed roles. It needs process engineers, it needs people who can create a plasma and use it to control the operations on a wafer in a chamber. We need people who can do a lot of characterization, who can tell if the DI water that is being used in your wafer dicing, is it having the right characterization or it needs to be changed. You need people who are safety specialists. You need people who can look at a vacuum pump operation and say, hey, it is not working right, perhaps there is a leak, and have the capability to detect that leak in that vacuum pump, who can identify parts of that vacuum pump, who can identify the faults, the symptoms, who can actually tell you how to create an ultra high vacuum for a semiconductor operation. Okay, those are the sort of skills we need, and I think today we are going to start the journey to give you a view of those skills. So if you actually go ahead, the perspective of skill programming at Electronic Sector Skill Council has been that you do need your foundation degree. Semiconductors is a multidisciplinary field. You will need chemists, you will need mechanical engineers, you will need electrical engineers, you will need electronics engineers, you will need computer engineers. Okay, it is a multidisciplinary field. So you start with your foundation degree, add certifications as you require to get into specific job roles. If you just take, for example, in safety, you just take the base safety of, say, electric safety or a HESCAM safety, you are an electric safety technician at a very simple level. If you add on the other modules of safety, you start moving up to becoming a safety specialist. Once you have done all the specializations, maybe some allied certifications, and you have also taken a certain experience, you become an expert. Okay, and then you have to maintain an integrity of your certification by, periodically going for a retest or revalidation by filing that you have completed certain experience, and then you are maintained in the system as an appropriate skilled person who can be leveraged by the industry. Uh, we will normally be covering all these characteristics in all these sections in today's program. But at the least, we are going to cover the HESCAM safety and electric safety. Some of the other programs maybe I'll do in the morning session tomorrow. The fact of the case is, uh, this is so let me actually take the case of what happened in February 1989. Okay, 1989, uh, there was a fire at SCL Chandigarh. Okay, SCL Chandigarh, as some of you may know, is the fountainhead of semiconductor program in the country. Uh, they uh, they had a loss of 75 crores in that particular era. Okay, 75 crores. Today's valuation in capital equipment cost could be close to about 3,500 crores. Its actual impact, India's semiconductor ambitions got thwarted for the last 35 years. Okay, the real cost of that particular fire. When it happened, there were a lot of newspaper discussions on what happened. Foreign hand, sabotage, management failure, CISF did not do its job, but technically it was what is known as a silane explosion. Okay, silane. Silane is an interesting chemical that you work with in in a in uh, in a semiconductor fab. Let me try and share a little more about it.
Warning, this video is literally...
So the semiconductor, silane is what is known as a pyrophoric gas. Can somebody tell me what is a pyrophoric chemical? Can somebody tell me what is an inflammable chemical versus a pyrophoric chemical? Inflammable chemical, you actually, sir. Inflammable chemical, you actually, you light a flame and it will catch fire. Pyrophoric gases will catch fire the moment they are exposed to air. Can you imagine? If there is something which can catch fire if it is exposed to air, how dangerous it can be to handle it, to transport it, to work with it, and that is what does happen in semiconductor industry. And do you know what is the safe distance if there is a commercial silane explosion? Tomorrow I'll show you a commercial silane training program, and the safe distance in case of a commercial silane explosion is 1.6 kilometers. Okay, that was what caused SCL disaster. And I think I want you to take the next few minutes to just get a feel of some of
Really
these
about
videos.
gases that ignite themselves simply by touching the air. Don't try anything you see in this video unless you know what you're doing. Aluminum phosphide and all the gases I'll be showing are toxic, and the acids used to make the gases are fairly corrosive. Gloves, goggles, and ventilation are all mandatory. Alright, let's talk pyrophoric gases. For the uninitiated, a pyrophoric substance is one which ignites spontaneously in the presence of air. Some solid examples include white phosphorus, certain alkali metals like cesium, and ultra-fine metal powders. And for pyrophoric liquids, most are organometallic compounds like diethyl zinc, tert-butyllithium, and alkyl aluminum reagents. Hopefully, I'll be able to do videos on at least a few of these soon, but for now, I'll be focusing on the big three of self-igniting gases: silane, phosphine, and diborane. And brief spoiler, things get scaled up pretty dangerously with some of the later contenders. Okay, starting off on the less toxic end, we have silane. Silane, or silicon hydride, is basically the silicon version of methane, and is probably the most common pyrophoric gas that amateurs deal with, simply because of how ridiculously easy it is to make. Its precursor, magnesium silicide, is literally made by torching magnesium powder with silicon dioxide, otherwise known as sand. In my case, I just scoop some dirt from my backyard and use that, after torching out the water and organic matter, of course. You can see the reaction isn't too violent, although, as Explosions and Fire pointed out in his own pyrophoric gas special, this isn't always the case. But anyway, once things cool down, all we have to do to get our silane is add a bit of hydrochloric acid. As you can see, it ignites with a nice pop, and we get this beautiful whitish fireball. Honestly, this is probably one of the coolest flames I've ever seen, and it lets off a decent amount of white smoke, which is just the silicon dioxide from the dirt reforming as the silane burns. Alright, next up we have phosphine. Similar to how silane is the silicon equivalent to methane, phosphine is basically the phosphorus equivalent to ammonia. This gas is honestly pretty terrifying on a number of levels. Not only is it pyrophoric, but it's also remarkably toxic. It burns to form corrosive phosphoric acid vapors, and thanks to its coexistence with other phosphorus hydrides, it tends to stink like garlic. So of course, the obvious question comes up. How do we make it? Well, all you need to do is add a metal phosphide to an acid. The metal phosphide I chose was aluminum phosphide, mostly because I had the aluminum powder on hand, along with a small amount of red phosphorus. In a process similar to the previous one, I simply loaded the reagents into a test tube and blasted them with my blowtorch until they reacted. This caused a somewhat more vigorous reaction to occur, and unfortunately, some of the phosphorus boiled off without reacting, producing a rather stunning tower of fire. Once things cooled off, I emptied out the product to examine it. Every once in a while, you can see a brief fire ignite in the crucible, and my best guess is this is unreacted phosphorus, which transitioned to its pyrophoric white allotrope under the high temperatures. Pretty neat. Anyways, once everything is ready, we can finally make our phosphine Breaking Bad style by dumping the phosphide all at once into a bath of hydrochloric acid. Alright, that was pretty satisfying. So let's do it again. Science is all about repeatability, right? This time, I move the camera back a little so you can get a better view of the fireball. Awesome. Just awesome. Okay, we've now come to our last contender, diborane. This gas is toxic like phosphine, and it has a weird, sweetish odor, but its extreme reactivity towards air tends to prevent these properties from manifesting themselves significantly. You'll see what I mean soon enough. There are a number of ways to make diborane, but one of the easiest ways is to react an acid with sodium borohydride. Diborane reacts with water to form boric acid though, so it's really best to use something like concentrated sulfuric acid when doing this reaction. Of course, there are a few issues with preparing diborane in this way, which became evident in my first small-scale test. The diborane ignited with a loud bang, and the heat of the reaction, not even the diborane burning, was enough to crack my vial and fuse some of the formed sodium sulfate to the glass. This, of course, prompted a second trial, which ended similarly. So clearly, this is a very dangerous reaction that destroys whatever it is put in, and releases an explosive cloud of noxious gas. Clearly, this should by no means be scaled. I scaled it up by roughly 10 times and used a whole lot more acid. This is unsafe, unwise, and come on, what'd you think I was gonna do? Yeah, that was pretty cool. Was it a bad idea? Yes. Did it total my flask? Yes. Will there be more mayhem to come? Of course.
So let me actually add to the warning that is there. Uh, Extremely dangerous experiment, not to be done at all. Uh, Actually, I'm sure he had very special flasks out there. Otherwise, the entire container can shred and explode. Let me repeat, some of these gases are not just inflammable, they are explosive. Okay, it's not just a flame that will happen, an explosion will happen. There will be a huge energy release that can happen. It's just too dangerous to work with. But it's important that people understand what we are talking of, and I think that should set the tone for this discussion. So let me take the next few minutes and quickly touch base with you the semiconductor manufacturing processes. Uh, One of them is the epitaxial growth. You work with the base wafer in a controlled environment in a chamber, and you are going to try and create a layer on the basic silicon wafer. It can be silicon dioxide. When you try to do it, you are going to be playing sometimes with silane, sometimes with some other gases. At the least, you have in this process an exposure to some of the toxicity that we talked about. You have the chemical vapor deposition as another process that you will be working with in semiconductor industry. Here you are working with precursors mixed with inert gases, which will be actually performing chemistries in controlled environments. You will have you'll be working with plasmas, ionized gases, create that plasma ball, work on a wafer to get a particular structure shaped out. This is actually again an area where you'll be working with highly corrosive, highly toxic, highly hazardous chemicals, and you need to know what those chemicals are, and then plan your mitigation and emergency procedures accordingly. You have physical vapor deposition processes where there is a metal target where you could be bombarding it with excited argon atoms. The metal molecules will get deposited on a wafer. The hazardous particulate matter dust itself is a danger. In all these processes, the danger is not just in the controlled environment that is there in the chamber. It could happen later on when you are trying to clean that chamber. You'll again be working with byproducts which could be dangerous, so you have to be aware of that. You have diffusion processes, and in diffusion processes typically you will be loading wafer into quartz containers, quartz tubes, which are surrounded by radiant heaters. Sometimes your parameter setting goes off, the quartz container, the quartz tube cracks, and that also creates a hazard back at the site. So you have to be aware of these risks as you actually plan your execution. You have photolitho process, which seemed very simple, where you can actually you take a wafer and you coat it with a photoresist and you expose it to light, and you wonder why and where can there be a danger. But you have danger in photolithography, because when you are using those photoresists, before you do it, you do a primer coating with something called hexamethyl disilazane, HMDS, which is highly hazardous chemical. Okay, you are handling PPG, MEA, polypropylene glycogen methyl acetate. You have TMAH, which is trimethyl uh, ammonia hydroxide. Okay, so TMAH. So you have all these chemicals that Sushobanji taught us in the last fortnight only. Okay, so you have all these hazardous chemicals you are handling, and you have to be very careful. You have to follow the discipline. It's not that you will not know of it, but you have to follow the discipline, because the danger is there in front of you, but you may not realize it. Okay, that container which is containing that waterish liquid could be an acid. Okay, so you have to follow the discipline that is there in the safety data sheets. You have to actually really realize where all it could be there. So this is typically what is there. You have a wafer coated with a photoresist that's exposed to a light, but you have potential exposures out here. The dry etching process, the etching process, which follows a typical photolitho process, itself can be a source of hazard. If you take the wet etches, you are working with chemicals which are highly corrosive, oxidizing liquids which are highly dangerous, right from their storage to their introduction into the facility, to the usage, to their disposal, is something that has to be watched at every stage. And it is not going to be the responsibility of someone else. It's going to be the responsibility of everyone who's actually entering that premise. Okay, you have to you have a whole lot of processes which are created to try and manage it. Okay, but the human process is one of the key to enabling the safety. Okay, you have dry etch process where you are going to actually remove materials through plasma or highly reactive chemical gases, ionized gases, which are going to work on the surface. These can create different types of structures. Wet etch actually creates what is known as an isotropic cut, where the reaction of the chemical is uniform on that wafer. So you actually see an exposure taking place in all directions. Okay, you have the anisotropic cut, which is actually dry etching, which is the plasma based etching, which is very very what do you call it, Sushomanji? Anisotropic, a very uh, vertical cut. Huh? Sharp side walls. So there you are. Okay, so it creates a very sharp side wall. It's not going to actually take an exposure all along cut in this 360-degree reaction. Very focused vertical cuts will come. So you have the ion implantation of dopants, and again this is also a risk. In the course that we have stipulated, we touch on arc flash training. Okay, and why do we touch on arc flash training? Because you can be handling very high voltages in a semiconductor fab. The ion implantation machines can be at 40,000 volts to 500,000 volts of operations, depending on the equipment you are using. It can actually be a big hazard if not handled appropriately. If people try and leave the interlocks disconnected, if they are letting the parts exposed. Okay, so this is again an area of hazards that we have to intervene in and make sure that care is taken at the plant level. Then you have the chemical mechanical planarization, where you are taking that wafer structure you have created. You have started with a base structure, you have added certain layers on it. Once you have prepared those layers, you end up polishing it, setting the base for the next layer to come in. That process, the planarization process, is a process where you are operating with slurries, which can have additives, which can have other supporting chemicals in it, which can be hazardous. So you have fine corrosive materials like silica, aluminum. There are metals like aluminum and copper. There are stabilizers like potassium hydroxide, ammonia, and these can again be a source of a hazard. So you have actually a whole range of you know hazardous chemical exposure in a typical semiconductor operation. These tables, which will be a part of the kit that will be available for you to download later on, capture it in a very brief manner. Again, because this is not this is primarily a primer, so just try and understand. At the silicon wafer production stage, you could have an exposure to silica dust, which can cause a respiratory reaction. Epi deposition stage, you have all these gases. Trichlorosilane is a version of silane, very, very hazardous. You have hydrogen, which is actually, hydrogen is a very dangerous gas. Okay, Kalpana ji is around. Anyone from IC around? No, Sushivan has just left. But hydrogen is very dangerous. So it can it's explosive. Okay, explosive means it's not just a flame that you have to worry about. It's a huge energy release that you're worried about if it uh, if it is triggered. And really speaking, it's the sort of thing that you have to take care that you do not put it next to, for example, a silane you know a cylinder, because silane is going to catch fire the moment it is exposed to air. And if you have hydrogen next to it, you know, it will actually explode. Okay, and hydrogen next to it means you know, hydrogen. What sort of an explosion are we talking of? First of all, hydrogen will move up to the roof, and when it triggers, the explosion is not going to be you know, it can blow off the roof. If it is not properly anchored, it can blow off the roof. That is the sort of violence that it can bring in. Okay, if the roof is firmly anchored, it can go from there to other parts of the building. Okay, so it's a pretty dangerous gas, and again, you have to understand the actual flow which could take place in a real life situation. And Gauravi is not here, but she would tell you in her session. Basically, you have to do a hazard assessment. Not just that I have put the controls in, but where the risk can come. And that is again something very important and part of the safety exercise. Silane, oxygen, nitrous, all these are there in the CVD process. PVD will have all the metals, so you have particulate material exposure. Process gases, again danger of explosion, ignition, breakage of tubes. All these are the issues that we talked of. The precautions can be engineering controls, it can be administrative controls. We'll talk of some of them as we go ahead, and really the discipline. So proper training and discipline is key to it. In litho, I talked of it. You have HMDS, the hexamethyl disilazine. So when you are coating the photoresist on a litho operation, most of us know that a photoresist will be coated. That is taught in the theory. But before you do it, you actually have to put a primer on it so that the photoresist can stick to the wafer. Okay, and that primer is your HMDS, and it is highly toxic. Okay, you have PGMA, glycol, methyl etheracetam, corrosive, TMAH, inflammable. And then of course you are working with light sources. You have to take care of your eyes. So all these are the sort of precautions and PPE planning that you do. PPE is personal protective equipment that you use while doing it. And etching is again the chemicals that we talked of, very toxic, corrosive, inflammable. You have something called a piranha etch, which is a mix of highly corrosive etchants with oxidizers in it that are used to clear the wafer, clean the wafer. Again, you have to take care when handling all this to follow the right protocols. Engineering controls can have robotics and automated systems, but really, long before you go to the engineering controls, you have to learn to do the manual controls, okay, and follow the right discipline, and to actually make sure that the right administrative controls are there. So if there is a shelf which does not have a GHS label, as we call it, I think it's a risk. It's a hazard. It's what we would turn out and say, okay, this site, this is an active point. Okay, So try and get all those things in place when you do it. It is absolutely in order to go around and take a look at a site and understand what are the safety risks. If you are a safety engineer, make it a practice. If you are not a safety engineer, anyway make it a practice, because safety is everybody's business. Okay, and that is one key message back there. Uh, Ion implantation, uh, we have talked of all these gases being used for dopants, and then of course the high voltages that are there, the hazardous voltages that are going to be handled. Slurries in CMPs can cause skin irritation. There are mechanical parts that are moving. They can create an issue if you are not careful. And all these things are just one simplistic view of the semiconductor processes. You know, you have to apply this thought as a thought everywhere in your execution of the program. So when I looked at the and we can miss it. So we looked at the wafer dicing national occupation standard that was made by IISc way back, and we were looking at a revision of it. Some of the thoughts we had was, hey, we need to add a little more on safety on it. We need to go beyond silicon and look at the other wafer substrates that India could be working on. So they could be working on gallium nitride, they could be working on gallium arsenide, they could be working on silicon carbide. Now those substrates are different. The silicon carbide substrate is a far harder surface than a CMOS surface. Okay, these are surfaces which have pins, pinholes, warps. Okay, so you have to provide for actually extracting dyes, creating dyes in the right manner on those wafers, and you have to provide for your dicing process in that. So you actually will be cooling your wafer, and you will be cooling your dicing blade to a different level. Depending on the application you are going, you will be doing a whole range of process to refine your execution. You might be back grinding it to meet the requirement of the thinness of the die that you need for a specific application. You will, if you are working on a gallium arsenide wafer, then you must remember that gallium arsenide has arsenide somewhere. Okay, it's not that there is a danger, because it is it's a compounded form now, but you can't just take that slurry, you can't just take that dust and put it straight to the ground. It's got to be filtered, and then it has to be properly disposed of. So all those things you have to take care when you are actually doing these executions, and a lot of these notes have to be read, to be understood, you have to go beyond what's there in the notes to be able to isolate what could be a possible problem. What will happen is, we are taking you through a quick view of the semiconductor industry process. Typically every fab will be a different manufacturing setup. Some principles are the same, but they could be, for their survival, operating on different materials, different recipes, creating different devices. Okay, so what we are saying here are an indication, but you have to adapt it to the actual environment and recipes that you are going to work for. Okay, so in fact, in the notes that we will give you, there will be one sheet which will say that this was a primer. It's not designed to be a substitute to a safety training. It's designed to actually get you appraised of the issues involved, but you still need to continue learning. Okay, and the safety officer has a very key role in developing this execution out. If you actually look at it, you will hear this term GHS a lot in chemical process engineering industry. Can somebody tell me what is GHS? Anyone? This job going for it? Quick, onto your mobile. No? Sushant wants to do it again.
Global health standards.
Almost there, not quite. So it is, GHS stands for Globally Harmonized System of Classification and Labeling of Chemicals. So it is not global health standards. It stands for globally harmonized system of classification and labeling of chemicals, and it relates to these symbols that you see on chemical containers across the world. And the reason this has come out as a harmonized system is because till about a decade back, till United Nations looked at creating the GHS, the classification of chemicals was not standard across the world. So if you take a look at Europe, something would have a particular symbol which may not be so obvious to an Australian, may not be so obvious to an Asian, and there was a need to actually bring about a standardization of that labeling and classification of chemicals. Worse, there were differences on what was considered harmful or what was considered safe. So something which US said is toxic, India said and China said it is not dangerous. Okay, and again there was a need to classify and have a standard way of classifying the chemicals that could be understood around the world. Okay, so this is why GHS was created, and it is one of the most fundamental it is one of the foundation of the safety safe handling and utilization of chemicals in the chemical process industry. So this is what facilitates international trade. This is what will enable a uniform management of chemicals. Hazard class is identified by the symbol. Okay, I'm sorry. Hazard class is identified by the symbol. But you have categorization of the severity from 1 to 4, and 4 is the most severe category of the hazard. So health and environmental hazards, the GHS symbols are classified in 3 different categories. So they are classified in physical hazard, environmental hazard and health hazards. So these 2 are obviously health hazards: toxic, harmful, cancerous, corrosive, irritant. Okay, this is environmental. You're seeing a dead fish and a bland tree out there. This is an environmental hazard. Physical hazards can be when it is an inflammable product, it is explosive, there is compressed gas, there is an oxidizer. Compressed gas can be a real danger. So many times you have cylinders, gas cylinders you are moving around with. Okay, they can have gases which are compressed by an order of 700,000 times. If by any chance that energy is released, that cylinder can propel like a missile. It can drive a hole through a wall. Okay, so you have compressed gas as a hazard, you have oxidizers. Okay, oxidizers can fuel a flame. So you never store an oxidizer along with an flammable chemical. So these are some of the nuances of the chemical safety handling. Summary in this, I'll not spend time on it, but you have to have labels like this on all the chemicals that are there. The labels will have a pictogram, the GHS pictogram. It will have a signal word which can be danger or warning. So what is more serious? Anyone, danger or warning? Danger. So danger is more serious. Okay, and then you have a description of the hazard, and you have a some precautionary statements there, and you will have an emergency connect statement there. That is on a GHS label for a chemical. This should be there on all the chemical bottles so that you are able to, or containers, so that you can identify what is all about. You have exposure limits for different chemicals. Here's one question back to the group. I've defined some terminologies here, very interesting ones. Permissible exposure level is 400 parts per million over 8 hours time frame. A worker is exposed to vapors of 200 part per million over 4 hours duration. Is she overexposed? Okay. Uh, but the exposure is less. Yeah, so it's like this. Uh, it could be true. Right now the data is not complete. Right now actually the data is not complete, but since you volunteered a response, your name, sir? Madhu Tiwari from Lam Research. So a respected name and a contributor to the ecosystem, I must say. Right now, the key thing is just that data is not enough to say whether she has faced a hazardous condition. Okay, you have threshold limit values, time weighted average. You have this interesting parameter called LD50, dose at which 50% of the test population will die, because most of these things are statistical probabilities, something which is immediately dangerous to life and health. And then you try and capture the information in safety data sheets for that particular chemical. So safety data sheets will have 16 information, which will be much more detailed, and you should have a safety data sheet for every chemical that is there on the fab shop floor. Okay, it should be accessible by the workers. This actually is something which the key operators in a fab, they should have gone through it, and they should possibly have addressed a few written exams in it, so they understand what they are dealing with. Any new chemical coming in it, its safety data sheet should be there by protocol. Okay, and the workers concerned should know about it. It should actually do the hazard identification, the first aid measures, the firefighting measures, exposure controls, stability, toxicology information, disposable notes, the regulatory notes, transportation information. All this is actually a part of a safety data sheet. Okay. In fact, at ISC, I saw something of interest. First of all, they were rigorous on it. Every lab I went to had its safety data sheet mounted close to the door. And there were some very interesting instructions. They said that if somebody has been exposed to a, let's say, a hydrofluoric acid, so after you wash and take the shower and whatnot, you apply the calcium gluconate and just grab a data sheet and rush to the Medicare facility. Okay, so that is the level of application some of these documents have. You store it in containers which are very clearly marked for it, which are actually accessible to people on the shop floor, and they're a key part of the administrative control on the site. Okay, so we should not take this lightly. This folder is going to be life-saving if there is an emergency. Chemical storage systems are not normal shelves. There are rules and protocols to actually store what you have to store, and you have to lot of time have very special shelves which are there for handling different chemicals. So if you are handling acids, you will have containers which will be you will be having shelves which will have lips. Any spill will not just go to the ground. You take care that acids and bases are not kept in the same container, same shelf space. You make sure that oxidizers and flammable material are not in the same storage container. Okay, so these are the rules, and they are special containers which are made, which are there in the site, and you make sure that when you deploy your chemicals, these are not deployed above eye level. Okay, if there is a shelf which is going beyond eye level, to us, we would say this is a tick, that there is something, or a cross, that this site is not meeting a requirement of safety. Okay, it doesn't matter you're wearing PPEs or whatever, but this is what will help make a safer site. Okay, you transport your chemicals appropriately. You do not put additional stuff in the fab lab. You only get what is required in the fab lab. Anyway, you're required to do it. If you're doing clean room, you want to have planarized airflow. If you put too much of, if you use it as a storage area, your clean room airflow planarity is lost. But even as a good work practice, you do not want clutter on the lab floor or the fab floor. Okay, everything in its place and a place for everything. That is the operating rule. And you make sure that all the containers are properly sealed. Okay, you're transporting chemicals not by hand but in appropriate, carriages. These are all things that the facility has to provide for. You can ask for it. If you think there is a need, you can ask for it. That is the rule of the game. So, safety tips of of handling chemicals in the workplace. Uh, how would you look at eliminating the chemical risks? Anyone? Before I go on to it, how would you look at eliminating chemical risks on a site? Uh, Bharti ji has got some of the answers right, but let me explain it in a different way. Uh, what I'm saying is, if you really want to eliminate chemical risk, the best way to do it is by eliminating chemicals. Okay, so like I said, do not carry unnecessary chemicals on the fab floor. Do try and eliminate the dangerous chemicals out of the process. That's one of the engineering challenges here. You can't do it always, but that's what the engineers work on, to try and create a safer process. Substitute safer chemicals wherever you can. Build engineering controls into the process, okay, which means you have interlocks that seal, do not let you access those chemicals, even by accident. You build up sensors that trigger safe conditions. Okay, those are engineering controls. You train staff on the process, on handling the chemicals appropriately. That's an admin control. Okay, another form of admin control can be, I want to limit my exposure to this particular environment. So you will say, instead of an 8-hour shift, I'll have a 3-hour shift. Okay, that is an admin control, and it is one of the controls which is exercised in fabs. Sometimes for hazardous process, they will limit the shift time to actually control the exposure to the chemicals. So you do all this, you do a rigorous job hazard assessment. Okay, and I will be having a speaker here shortly who is an expert. She will talk about it. So, engineering controls I talked of. You devise your process, equipment, ventilation, abatement, everything to control or eliminate the hazard. So, abatement systems are exhaust hoods. I saw one of the engineers, chemists at ISC in the last fortnight when we were taking a training out there. She was so good. She took care to close the exhaust hood, the wet bench hood, when working on chemicals. There are people who don't do that. Okay, so you're working on what you think is safe. ISC is given a very good safe environment, but if you don't close it, you are not following a safety practice. So she was doing it. Of course, people will, larger facilities will provide for automated wet benches, robotics to handle the wafer boards. But like I said, you need to be fully aware of the manual processes also. You have interlocks which can shut down a tool if the doors are open. I had a tragic situation in my early part in my career. I was working in a company called Metalbox, and they make containers. And they make containers by taking tin plates which are bent into a cylinder in a can and then cut, and then those are being used for manufacturing. And for some reason, that flow of cans is of the plates is very, very fast. It got stuck. The factory manager who was there, he tried to remove that tin plate by his fingers. It got moved, and the entire line started working again at a pace. His fingers got cut. Okay, you have to take care of these things. Remember, your fingers are counting on you to be playing it safe. Okay, so this is why interlocks are relevant. You can't just if there is an engineering control, sometimes you feel that's too much of a issue. I want to ignore it. I'll shut it off and I'll work faster, but it's too dangerous. And then there are toxic gas monitoring systems that I shared off, which can trigger controls if they sense that there is a there is a toxic gas leak. A lot of times, you yourself will not be able to detect a toxic gas leak. Not everything will give you an irritant response. Okay, some of the gases, arsenic is in parts per million. So you have to respect that signal which comes from the sensor, and you have to evacuate as soon as you have that signal. So you can build up all these administrative controls. You have to take all these cares. You have to do a job hazard assessment rigorously and periodically, and then only can you actually move towards a safer site. Training is a key part of the exercise. Following the right principles make a lot of difference. In my original thing, I talked of PPE as one of the last resort stuff. If you remember the entire safety enablement process, PPE is the last resort. It's got to be done because somebody has to handle that particular hazardous incidents. For that, it has to be done by trained people with the right PPE, and that right PPE has to be tested at every stage periodically, otherwise you are possibly having another exposure. Sulfuric acid is another example I am taking in what could be an exposure. Highly corrosive, colorless, slightly yellow, soluble in water in all concentration, used extensively in semiconductor gate. It's one of the highest pure in its purity pure form, ultra pure sulfuric acid and ultra pure HF and ultra pure HCl. They are used in your Piranha H's, wet H programs. If by perchance you touch it, it can cause severe burn. So ideally you should have those chemical safety gloves, aprons, eyewear, safety eyewear, and you have to have in that facility showers, safety showers, so that in any such incidents, on the spot itself you start washing it off, and you can really control a lot of the damage if you do it immediately, and then follow through on the subsequent process. The hydrochloric acid, same thing, I will not repeat. These are some of the PPs. I don't know if you know this guy out there, anybody? Okay. So there you are. That's me, and you really need to take care. Acid exposures, these are the sort of showers and eye wash balls that are there. They have a reason to be there. So in the event of a chemical safety incident, there is a procedure defined for the qualified person to actually secure the spill after containing it, cleaning it, and then disposing it out. Like I said, this is not going to be anything more than an appreciation session, so that's why we'll not get into those details, but a question back. There is a room of the size of 10 feet height, 10 by 10 length and breadth. Okay, there's a worker, that's a gas storage yard, say. Okay, and that room, and the worker is carrying this nitrogen gas cylinder. Okay, 20-liter nitrogen gas cylinder. The worker trips and accidentally releases the nitrogen in the confined space. What is his risk? You know. I know you know. So anyone else? What is the risk? There's a chocolate waiting. You can be right or wrong. Why? This nitrogen is 78% of the air around us. But you are right. You see a 20 liter nitrogen cylinder. multiply by the coefficient of expansion 700, 14,000 liters in 1,000 cubic feet area, 14,000 cubic feet of nitrogen, your percentage of oxygen comes down dramatically. There is a condition called apoxia. You can't breathe. You need to have at least 10% oxygen for human body to sustain itself. So, if there is an accident like this, there is a risk, okay, and hazardous waste is a risk. It has to be disposed of properly, not just for your own safety, but for the safety of others who could get exposed to it. Byproducts in maintenance can be a risk. They have to be followed with the rigorous procedures. Records have to be kept, and I think it's a very specialized role that is there. I would like to call a specialist who's actually involved with one of the biggest semiconductor companies in the country, in the world, to come and take the floor and take this session ahead. Gauravi, your audience, your floor. This is the disclaimer I was talking of. Laptop or USB?
Good morning, everyone. Am I standing between the coffee and a presentation? Okay. No charger required. I'm fine. Okay. This is Gauravi Lokhandwala. I work for Applied Materials. I lead EHS function for Applied Materials, and with Applied Materials for last 7-8 months. Prior to that, I was working with the aerospace industries and then healthcare industries. So overall, I have 17 years in EHS, and that's my bread and butter. So whatever you ask in EHS, probably I will try to answer all of your question, or I will try to get an answer for you. So there are two options that we have. So you can ask me any questions on the environment, health and safety, sustainability, anything on the process chemistry, process related management system, abatements, chemicals. We can talk over and over about all of those aspects. Talking something more about applied materials in India from last 20 years, and this is our vision, mission and value. We want to innovate better. So first of all, what is applied materials? I think one of the tasks that has been given by our country head, that when we say applied materials, we should not be explaining what applied materials does, but I would take an opportunity here to explain a bit. Applied materials manufactures the equipment which is used in semiconductor industry to produce a chip and a fab. So that's basically, we are the backbone of a semiconductor industry. We do a lot of R&D, research and development. We do manufacturing of machines. We also do the field service for the fabs and many more activities overall as far as the India and other part of the world concerned. And we are a US based organization in India, in couple of cities. We will go through that. What we want to do, our vision is we want to be a most valued partner. We wanted to be at a mission to lead the material science to the fullest, where we enable the customers and transitions with a possibility into reality. We have our 4 core values. Most valued partner, we want to be together as a winning team. We want to be responsible and integrity, and the world class performance. So these are the 4 basic kind of values that applied materials work with, and we live by it. Where are we in India? So we have a base location in Bangalore. We have 2 locations in Bangalore. We call it as an IVC and ITPL. ITPL has lot of labs. IVC also has one of the lab. We are in Coimbatore, Chennai, Mumbai, and Pune. Pune is a small kind of office building, and there are some kind of other R&D activity which happens over there. Um, these are the kind of labs that we have. Exploration Center, which is in Mumbai. Reliability Lab is in ITPL. Concept and Proto Lab is also in ITPL. India Validation Center is a new process lab that we have developed, and for which we are very proud of. That's basically, we talk about all the tool process chemistry when we speak about a different way of managing the processes, how the whole fab area look like and how the chip gets manufactured. So those all experiments, innovations, R&D all happens in our India Validation Center, many of those. We have 13, 14 tools that have been installed with many of the metallurgical instrument, where we do a lot of understanding, stress analysis on many of the data which is required for our R&D center to be more effectively working on. EHS, now coming to my core. So EHS is very simple. So when we say that there are a lot of chemicals and we have to take care of this and we have to take care of that safety, no, it's not so complicated as we think. It's very simple. As simple as, if you think and if we feel that there is an hazard associated with, find out a control related to that. It's very simple. Do not leave anything without control. Say simple thing, when we walk around, there is a yellow tape. So it remembers, it gives me an understanding that I have a step down, right? It's as simple as that. If there are no steps or there are no yellow tips, I may not see and then I might fall. So as simple as that. So EHS is absolutely very simple function, and we do not want to make complications. The only thing in EHS, we need very good electrical, mechanical, chemical engineers with the safety background. That would suffice the overall purpose of the safety function. When we talk about the vision and mission of applied materials of an EHS, we want any employee that come inside our premises, we want him to go back home safely. The way the person have come, the person should go back safely, healthy. Okay, so that's the basic vision and mission that we have. We also wanted to become a pioneer, and we are a pioneer in many of the safety systems in subfabs and the entire semiconductor industries, where we provide information and awareness about EHS to others and we learn from others. So that's technically our vision and mission. Now, how do you integrate overall EHS perspective into your fab area or subfab area? This is very simple, right? This is what we call is a tool. What is tool? Tool is where the all processes happens, right? All the chemicals comes here. Now it comes through different kind of pipelines. Now where the pipe arrives? The pipe is arrived in this particular gas bank, where we have put the gas cylinders, right? So this gas bank has a gas cylinders and it comes from here to this path. Now when you put all the gas cabinets and gas banks, we need to have enough controls in place. So if there is a pyrophoric, let's take an example of pyrophoric. It's an easy because sir have explained that in detail. Pyrophoric is a gas, when it comes in contact with an atmosphere, it catches the fire. Just imagine I have a cylinder kept here, a pyrophoric. So what should I do? I have kept a cylinder. The cylinder should have a hose and the pipe should run. Now I should not have a leakage, right? How do I avoid pyrophoric coming in contact with an oxygen? To avoid the leakage. So all the pipeline that I have done from my gas bank area to the sub gas bank area should have a double coated SS steel, which would not corrode, neither it leaks, right? That's a simple thing. Now if it is leaking, we have a, so when we talk about ppm, another point I would take, ppm. So pyrophoric, we call it as a PEL value. So 4% release into atmosphere catches a fire. So I will put my detection system, which is what you see, the small thing which is on the top of it, the small system at a 25%, which means when it releases at a 1% atmospheric pressure, it identifies that there is pyrophoric leaking. When the pyrophoric leak, that is detected, identified and linked with the SCADA system and a gas bank. What does it do? Shuts down your gas deployment further. As simple as that. Such an easy safety system, right? You want to use a gas, have a pipeline to the tool where the pipeline is connected and identify what is a PL value, what is a PPM value, what is a TWA value, make it 25% of it, and as soon as it releases, do the detection and shuts the process down. How many processes you will shut down? You will shut down the gas bank, you will also shut down your primary gas bank, you will shut down your tools, right? Because up until here is your inlet of a gas. Up until here we are here. Okay, so this is about one of the safety system that we had defined in a subfab area where we handle the chemicals. Now we are here. Again, the chemistry happens. When a chemistry happens, silane, let us take a silane. Silane connects with the argon gas and make silicon oxides, oxygen, and make a silicon oxide, and then it releases hydrogen into the atmosphere. So what is the byproduct? Oxygen and a hydrogen. Now when oxygen and hydrogen comes together, there is also possibility that not 100% silane is going to utilized in the tool, right? There might be some unreacted silane. So other silane also will come out. So what are the gases came out? 3: hydrogen, oxygen, and not reacted silane. So when these 3 things coming out here, you cannot let it go to the atmosphere because silane will catches a fire. Hydrogen is again a flammable, it catches a fire, and oxygen helps them catching a fire because oxygen is there inside. So this is a system called an abatement system. What do you mean by abate? Simple English. Abate? Exhaust or destroy. So the chemical uses a different kind of mechanism which destroys a particular kind of a chemical. So silane comes in the contact with the water or the mist and also with some kind of a plasma or the electrical heat, and it gets destroyed, right? And the similar way oxygen get destroyed, similar way hydrogen get destroyed, or hydrogen get combined with the oxygen and make an H2O. So this abatement system is where we utilize whatever the gases which came out from the tool, which goes to the abatement system, and from there the abatement system, it gets into the dilution of a water. Now this water which got diluted into the abatement go to the effluent treatment plant, and the gases which have been kind of chemical molecularized, those chemicals and the gases will go to the scrubber system, which is called a secondary scrubber. So you have two things. One is point of view scrubber system, where you are 99% of the gases are getting into the chemical molecule position and it is getting destroyed, and whatever is the 10% or whatever is the 1% is remaining going to the scrubber system and it released to the atmosphere. It's a very simple. EHS in a semiconductor is very simple if you know the basic fundamental of a chemistry. So when we understand about the chemistry, when we understand about the overall perspective of a safety system, this is how the usual safety system works. This is a preliminary design of one tool. Along with that, if you are using a 7-8 chemicals together, do all the chemistry, identify the chemicals which are going to work along with the tool, what is the chemistry happening, how much percentage it is getting reacted into the chamber, how much percentage directly comes out, right? So these are some of the activities that we do in a semiconductor industry before the fab comes out. We do all this testing. How do we do the testing? There are helium leak check for the gas line, pressure gas testing for the gas line. Gas panels has an exhaust system. The exhaust system should have 5000 CFM, 200 CFM, all combined should. So it's more about mathematical chemistry which would ensure that overall safety systems are followed. So are we okay with the first line of semiconductor safety? Any question on the slide? Okay, no question, good. Okay, switching a gear from the safety on the how to implement versus what to implement. What is a very important thing for us is a management system. So when you have to run any of the program into the system, and when you want to have an industry, and I am sure industry experts here would definitely acknowledge that, you need to have a management system. Management system would tell you how the industries best can run. So what is the base of the overall management system? The compliances. India has overall 140 to 150 regulations, rules and act, which are either way, some or the other way applicable for the semiconductor industry. Now we as an industrialist, we have a job to understand what are the compliances that we have as part of the government requirement. As simple as that. If you want to set up an industry or a factory, you need to have a factory license. If you are setting up an R&D center, you need to have a shop and establishment license. If you are working with the water which is generating from your process, you need to work with pollution control board to get the license. If you are going to work with the workers greater than 10 people in a floor, you need to have a factory license with the set of requirement, the how workers are going to work. So it's not easy. So when you are not making, when we are making an effort to have an industry to be placed in a Karnataka or any part of the world, you need to have a compliance as your base and ensure that all the compliances have been met. Apart from that, there are 4 pillars that we talk about: the policies and the procedures. PP policy, EHS policy, sustainability policy. There are a lot of policies that you got to make so that the employees who are going to come and work with you are all aware about the policies and the programs that you have in place. The second pillar is a program. When I talk about the first slide, that these are the gases, this is the chemistry, here are the PP, these are the detectors, how would that work all together without having process in place, right? So the most important thing for us is define a process. To run the EHS management system smoothly, you need minimum of 45 to 50 procedures just to run the EHS management system. Start from your EHS policy, PP policy, inspections program, compliance program, contractor management system, machine guarding procedure, electrical safety procedure, hazardous waste management procedure, air, water, waste procedure. So all procedures come together, you need 45 procedures, right? When you have a 45 procedures coming together, making that a sum of a overall management system, that's when you will be successful in implementing the programs. Risk assessment. How do you do risk assessment? Simple. Walk your floor, understand the tool, understand the process that you are doing as part of an industry, and identify what are the risk and hazard associated with it. And why do you want to do that? Just to ensure that the employees who are coming and working with you are safe, right? So the risk assessment is a very, very top-notch activity as far as the semiconductor industries are concerned. How do you identify the risk of chemicals? By conducting the risk assessment. How do you identify the PPE value or TWL value? By understanding the industrial hygiene exposure limits. How do you identify that here is a problem and you got to fix it, where there is a leakage? By conducting the inspection program. So these are some of the risk assessments that we have to do, and all this risk assessment coming together make one of the pillar which is required to run your management system. And last, not the least, audits and inspection. All the audits. So PDCA cycle, you might be knowing about ISO 14000, ISO 45000, ISO 51000. Those are nothing but an audit. So every industry have their own audit methodology or the process, or you follow ISO related activities where you identify what is the programs that you have, are you really in compliance with it, and are you following or not. That would help all of your entire system to run efficiently and working fine, and that can only be achieved if you have a support from your leadership team and a management, right? So the top of a roof is your leaders, your managers, and the people who are working for you, and process and procedures are your pillar, and the base is your compliance. That's make your EHS management, sustainable EHS management system. When we talk about why do you need a management system, right? Why do you need so many procedures? Why I need for 50 procedures to run my EHS program? You don't need one, right? I know how to do this, I will do it. I know how to do that, I would do it. The only problem is when you have person dependent processes, when the things are dependent on a person, it's very, very challenging, because if a person is not there inside your premises or a person is on vacation, your thing will not go, which means you need to have some kind of process and procedures which would required for your organizations to run. And the first and foremost is, it's for the protecting industrial health of a worker. So anybody coming to your premises, let's take an example of silent gas. Again, the person have come, there is an explosion, and a person have a burn in his hand, a small burn in his hand. Are we impacting a person's life? Right? We are impacting a person's life. So what is most important thing for the management system? If you have done the risk assessment, if you have identified the risk associated with it, if you have put engineering and administrative control, if you have provided a PPE which is required for a worker to execute the job, if you have done the right inspection of a tool, if you have done an audit of a overall system that you have implemented, you will have not leak of a silent gas. And that's exactly what we are looking for, right? So if you are protecting the, how do you protect the health of a worker? When you implement the right system in a place, and which is very, very important. And how do you protect it? By implementing the management system. Compliance and the regulations. Every industry, as you walk in, you need to have a legal register or a compliance register, a list of laws and the regulation that is required for your industries to run. If you don't have one, it would be very challenging for you to run your industry, considering every day the rules are changing now. The government is becoming more vigilant, they are becoming more digital, so you need to be on top of it. Identify and reduce the risk and liability. So risk assessment is one of the easiest process. Identify the risk and liabilities. Corporate social responsibility. So if I work for applied materials, and I'm very, very proud that in India we did not had a recordable case, or we did not had a day away from work case, right? That itself says that how safe we are working, and how great the industries have put an effort in the EHS function. As simple as that. So the responsibility, so when I say about applied materials, the Department of Factory understands that. Oh, these people understands the safety system, they have process in place, they understand, and many of the area we go as an expert to Department of Factories and Pollution Control Board to talk to them about and give them an information about this is how it works, right? So this is where the applied materials play a vital role, and that's when you need a management system. Drive operation efficiency and effectiveness. Now, many people ask me a question, if you are in EHS, how do you say that you can drive the efficiency and operations? How can I drive? Very simple. A person met with an accident, your tool is down, person will not be able to come to the office for 1 week. So if the person would have not met with an accident, he would have still do the production, right? So if I would have implemented enough safety system, and I would have done the checks and balancing of my safety system, which means my person would have been saved, which means the productivity would have not gone down. It's absolutely related to the safety system implementation with the productivity. Now, business continuity. If your tool is down, your business have a continuity issue and it will not run. And the last one is a sustainability. Sustainability is a big subject, and it's a little different than the safety, but sustainability is basically understanding more about how much waste you are generating, how much environment you are polluting, and how much air that you are generating, which can be abated, which can be reused, or water can be reused into your system, and identify the reduction in terms of the energies that have been utilized. If you have done the management system implementation, you can also achieve the sustainability overall. There are so many certifications in a sustainability that we work on, but we will talk about later on sustainability whenever there is a time permits. Now, how do you implement all the procedures, policies, programs, audits and inspection? Simple. Define a policies and a management program. Then do the planning. These are the planning I want to do. I want to identify the goals and objective for the year. I need to run these programs. I need to identify the legal register, and I want to do a risk reduction plan. These are the only 5 things that you require from all the procedures and program. And then go ahead and implement those 5 things onto your floor. When you implement those, you are going to get some actions. And when you get an actions, you need to do the performance measurement and the audits and inspection for the programs that all of those that you have implemented. Review with the managers, leaders and the leadership team members. Make leadership team members accountable for the activities that you are performing, which would have documented procedures and program for your leadership to review the progress, that how are you performing on year, what is your strategy plan for 5 years, and how are you performing on every year, and how your leadership team is getting engaged on those 5 years, which also requires a budget. So if you are looking for a real implementation of a safety system, you should also have an EHS and a safety budget, and definitely you got to work with your leadership team on the implementation of a same. Now, I have spoken about management system, I have spoken about the risk. Until and unless I don't have a right culture in my organization, how will I drive safety? Very important, right? I have a program and a procedure. So this is a program, I have trained a person, that person is aware, there are engineering controls put in place, but my willingness is not there. I am not willing to follow any of the things which have been put in place. It's an individual's decision, it's my decision, I don't want to do it. That's when the safety culture or the organization culture come in picture. What do I mean by culture? Culture is the way we drive, we live, the way we live at our home, the way we live in our organization. That's an overall as a part of a culture. To initiate the cultural program, Applied Material have come up with a methodology or a philosophy called HOP, which called Human Organizations Performance, where it's a philosophy where we are very clear. We think that human will do the mistakes. Do we do mistakes? Yes. I would have done a lot of mistakes in talking this for 20 minutes on some English grammatical mistake. I would have skipped something which was required to be put in place, right? Everyone does lot of mistakes. Now, how do you make your process and policies strong enough where then you don't allow human to do the mistake? Your engineering controls should be strong, your administrative controls should be strong, where you will not let any human to do the mistake. That's the very first philosophy of an HOP. Second, blame, fix, nothing. When we have a siblings, what do? I didn't do it, he might would have done that. Simple, because it's easy to tell somebody else have done it, right? So blame, fix, nothing. If you are telling somebody to fix, if you are blaming someone for the mistake that have been done, which means that person is depressed, the person will not be able to talk about it, the person will have a depression mindset, and the person might not perform the way it has to be for, right? Learning is vital. What do you mean by that? 10 years before we were not talking about semiconductor industry. Today we are talking about semiconductor industries, right? If we would have not put an effort in understanding pyrophoric hydrogen, silica gel, silica, SiO4, SiO2, the plasma, the anodes and cathodes, if you would have not put an effort, we would have not got the wafer out. And if you would have not got the wafer out, we would have not got chip out. As simple as that. So learning is very, very vital and very essential in any of the process or the progress that we do. Context drive the behavior. Sometimes someone comes to us and tells some stories, very simple, okay, something like that happened, I went there, something that happened, and we say, okay, I understood, it is your problem only, you were the person who does not follow the process. Which means we did not understand the context of the whole story. Before that only we are saying, no, it's your mistake, or before that only we are becoming judgmental by stating that, no, I understood, you are not required to explain me. So when we become a negative in the context that we are driving as an overall perspective, that does not work in an industry. If a worker have done something, you got to understand why worker has done something, because that could be the way that he is performing, and we are the one who are not aware that the work is happening that way. So for example, if I have to walk from here to there, I may walk from here to there, I may step down here and walk from here to there. It's my wish, until unless you have not defined the process, right? You define a process that a person have to walk from here to there, take 8 steps, and there are 2 steps down. That's when you would say that, okay, the process is defined, the worker have not followed. Now that is long for me to walk, I would just walk from like this to there, right? Just a crisscross. That's a normal for me to walk, because I'm walking a 15 steps to go there. With this I'm walking only 8 steps to go there, right? Which means that becomes a normal way of a worker. So you understand the context, the way the worker is performing the job. Okay, now this the last principle says how you respond to failure matters. Nowadays there is a new program which is launched in India, right? How to talk to your kids. Earlier it wasn't there when we were there. So our moms were like, don't do that. So now we cannot talk to our kids like that. We have to be humble, we have to be polite, we need to understand the context, isn't it? Yes or no, right? Okay, so that's how you respond to the How you respond to the failure does matter, which means an accident had happened or somebody have cut the finger and you are shouting on a person, hey, you don't know how to do the operate the machine, you have to understand what it is, you didn't follow the procedure, why did you touch your finger there, you were not required to put your finger there. The person is losing the motivation, the person is gone. He will not tell you the story what exactly had happened in the incident. You will never be able to go to the root cause analysis of an incident. So first and foremost things, just make yourself cool and calm, then talk to a person that, hey, how did it happen, was there a problem, how do you fix this, do you have something for us to tell, can you tell me, can you make me understand the process. We go there as an expert. However, we were not, because the person who is working on that particular equipment is an expert. He runs the equipment, he runs the process. You are just a supervising a person. So you go and become an expert when you and don't listen to an expert. That's when the way you respond to the situation really matters, right? So these are the, I would leave you with all these 5 principles of an HOP and a culture that we are trying to drive in applied materials as a global. And that's my last slide. I just wanted to thank everyone for giving us an opportunity to come here and talk to all of you. So thank you. So we hire electrical engineers, mechanical engineers, electrical mechanical engineers, chemical engineers, environmental graduates, chemical graduates, because these are the core team. So I have my core team who has this 5 different kind of engineers and the graduates to whom we work with. So if you think that what is the future in this is a hot piece of cake at this moment. Okay, so just understand, get your education from the right institute, and reach out for any help that you need in the future. Thank you.
So, Gauravi, thanks for that. A small token of our appreciation. I just repeat, the beauty of this particular job role is the content trains you for semiconductors, but it is portable across any chemical process engineering industry. Okay, I have made sure that it is a part of Manarachna's semiconductor training program next year. It's an option. Okay, as far as possible, try and build it in your institute's programs. Ask for it. Get your board of studies faculty, get them to take a look at it seriously, get it in. There are jobs here. Okay, cheers. Let's break for tea and we'll come back in 15 minutes time.
Flip chip bonding. Wonderful. Something else? Dicing. Who said that? Super. What else? Wire bond. What else? Okay, TSC. What else? SIP. SIP is a type of product, right? What are the processes? Yeah, I think the guy at the back said that. Anything else? Yes, Hanji? Correct, grinding, polishing. That's especially important in memories. So, some of you guys have seen this, not a bunch of you guys. So, I'll do a very quick thing. I'll introduce the company, and then I'll walk you down our process for packaging. We are primarily in the discrete and power discrete products. So, if you give me a second, I will just give you a quick video which will walk you through the company, and then we can get started on the process.
CDIL has been a leading light, illuminating the way for India's semiconductor journey. Our transistors, diodes, MOSFETs, and other semiconductor devices have played a pivotal role in advancing India's electronics sector. From budding engineers to seasoned professionals, CDIL's components have empowered countless companies and individuals, turning their ideas into reality. From the
Okay.
light
This is okay, you can read the text here. Captions का फायदा है.
and ACs in your house, to your car, to our national railways and even the country's space programs.
Did it
You may
stall?
not have known it, but CDIL semiconductors is and
There
even
we
the
go.
country's space programs. You may not have known it, but CDIL's semiconductors have allowed them all to work smarter and more efficiently. The story of every CDIL device starts with our engineers who use their expertise honed through years of wafer fabrication experience to collaborate with top-tier chip foundries and craft high-quality wafers. These wafers arrive at our assembly, test and packaging plant located in Mohali, Punjab.
So you'll see the packaging process start now.
The plant features 10 semiconductor packaging lines and a skilled workforce of over 300 professionals. After arriving, the wafers are mounted onto a mylar adhesive and carefully cut into individual dies using a diamond-edged blade.
Dicing.
In the die attach process, a bonder uses a digital wafer map to pick up good dies from the wafer and attach them to a copper lead frame. Gold, copper or aluminium wires are then used to connect the die to the terminals of the device using ultrasonic and thermosonic precision arms. For high voltage devices, a special state-of-the-art clip bonding technique is used in place of wires for better reliability at high currents and temperatures. The lead frames then move for encapsulation, where a protective molding compound encases the package, ready for it to be singulated into individual devices. Each device is optically inspected and put through a stringent 200% electrical testing plan, ensuring that every part meets or exceeds its device specifications. Qualified parts are laser marked and packed in an integrated inline system. At CDIL, quality is not just a commitment, it's a tradition. In our cutting-edge automotive and aerospace high reliability lab, we rigorously stress test each lot under extreme conditions, including rapid temperature fluctuations, high humidity environments, corrosive atmospheres, and intense acceleration forces. These exacting standards ensure that every component consistently exceeds the highest international benchmarks for performance. The final devices leave our facility and head to our customers to get assembled into their products, powering the next set of innovations in consumer electronics, transportation, solar energy, and more. With India's growing leadership in electronics manufacturing, CDIL is investing heavily, increasing its capacities and pioneering R&D on emerging technologies like silicon carbide to push the boundaries on cutting-edge devices. Today, CDIL's legacy is not just its components, it's our dedicated team, from engineers to support staff, who are the driving force behind our success. From wafer to final packaging, CDIL's commitment to excellence is evident at every step of the process, empowering tomorrow's technology today. CDIL Semiconductors. Legacy, quality, trust.
All right, so that should have given you a very quick there we go, hang on. Who was I telling that you can do cutting edge semiconductors, but you can't do a presentation without a glitch? Okay, so that was a quick overview of what the packaging process looks like, and what we'll do is we'll dive into each of them very quickly and just talk about a few parameters that are important for each process, and what are some of the things that we look at when we're assessing if that process is going well or not going well, right? What are things to look out for? What are things that you need to pay attention to? So this is the product range that we do. These are primarily all the discrete products. In the discrete products, you have your standard transistors, diodes, MOSFETs, voltage regulators, TVS devices, Schottkys, etc. And more we're moving into the power sector. So the power segment is now silicon carbide. It's looking at high power MOSFET, Schottky barrier diodes, and this segment is a segment we see a lot of great gains in India. Any place that requires electrification, conversion from the grid to a battery and a battery to some other product, you require power electronics, right? For faster charging speeds, higher currents, higher power, you need to start moving to power electronics. So on the power electronics side, what are the places that require a conversion? Biggest opportunity for batteries, EVs, super. In a country like India where the grid is not amazing, where else? UPS, stabilizers, solar inverters, there's a huge opportunity here. So this is where our focus is moving into. As I mentioned, we've got 4 units. We've got an EMS facility and semiconductor facilities. For the semiconductor facilities, they're in Mohali. Reliability testing, etc. Why don't we just move to the packaging side now? Just some sectors that we're working with. Right, perfect. Okay, how many of you guys can spot the discretes? How many discretes are on this page? In this one diagram, how many discretes and how many logic or other processors? Anyone? More than 5 discretes, raise your hands. So, more than 10 discretes? Yeah, of course they are. All these are discretes. These ones here. So every one microprocessor, etc., needs to have the current and voltage that makes it run properly. And you need discretes to monitor that and to regulate that. So for every one logic board, logic processor, microprocessor, control unit, you need a bunch of discretes that regulate the voltage and current it's getting, because if you were to plug your, say, phone or laptop directly into the socket without a power brick that converts and regulates what's coming out, it's not going to work, it's going to fry the chip. Clear? So discretes are important. They may not be as high-tech, cutting edge, but without discretes, nothing works. So this is what ATMP or OSAT works. You have the wafer, which gets designed. A lot of the designing happens here in India. After that, it will get fabricated. The fabrication happens in multiple places around the world. Most of you guys would know TSMC. It's a big wafer fabrication unit. And then after the wafer is fabricated, it needs to be processed into something that's actually usable. You can't use the wafer directly, it needs to be put into a casing, a packaging, something that works and then can be handled so that it can be put onto a board. That's what ATMP is, assembly, test, mark, pack. And these are roughly the simple processes. So you have the wafer dicing, you get the wafer, and you cut it into, I'll walk you through it. So wafer dicing, die bonding, wire clip bonding, encapsulation, lead finish, testing, marking, packing, reliability. All right, wafer dicing. So when you get a wafer, the wafer is a disk, right? There are multiple die on the same wafer, and you can't use all of them together. You have to singulate them. They have to become individual pieces. For this individual pieces, you actually are cutting the blade. Now, if any of you have seen a wafer, how thin is it? Excellent. Do you think you can just cut it without too much breakage, chipping? I mean, it's difficult, right? So what are some of the key parameters when you're looking to cut? The blade type. So what we use is a blade technique. Some people use a laser technique for dicing. We use a blade technique. So the blade type is generally coated in a diamond, diamond grit. The grit size, the strength of the blade, the thinness of the blade, the thickness of the blade, important critical factor. Then again, you cannot just cut it. Why? You need to avoid thermal stress. So how do you do that? You pass water through it. Can you imagine you're putting water on electronics? How, can anyone tell me how that works? It says cooling water. Can you imagine putting cooling water on your electronics? We're told it's a no-no. Why does it work here? It's deionized water, right? So even the water you're using has very critical parameters without which your process will break, right? You'll start getting defects. So for this industry, you will start seeing, as I mentioned earlier, you're looking at complex systems with a huge number of variables, and I'm just pointing out a few. So before dicing, we have to measure the resistivity of water to make sure that it can actually be used, otherwise we'll have a ruined batch, right? So at every step, there are more and more parameters that need to be understood, and as you understand them, how they interact with other parameters becomes critical. And that's really the fun in semiconductors. So you'll have a blade running. How fast is the blade running? How fast is your wafer moving across it? These are all parameters that need to be controlled. For different material, the parameters will be different. If your wafer thickness is thicker, you may be able to go faster. If wafer is thinner, you may have to go slower. If your wafer is more brittle, for example, silicon carbide is a very brittle material, you will have to completely change the parameters to avoid chipping. So kerf width. Kerf width is what you call as the width between two dies. So if you see here, you can see that line in the center. That's the cut and how clean the cut has to be so that you don't damage either one of the dies. Right? So what are some key considerations? You need to avoid mechanical stress. You're cutting something at a very high speed. You need to make sure you cut it smoothly without cracks or any damage to the die. You need to minimize the kerf width, so you accidentally don't cut into the active parts of the die. Your blade has to be monitored for wear and tear. If you keep cutting and you don't sharpen it in time, you will have issues. Particle contamination, you're cutting things. Anytime you guys have cut something, you'll see there's a lot of debris. You have to make sure you remove the debris. And that's part of where the cooling also comes in. And again, managing heat generation. Some key pointers for dicing, how you control them, and what are some key considerations. Now we move to the die bonding. In the die bonding, it's fairly simple. You have the die that's been singulated. You'll have an arm pick up and place it onto a lead frame, right? A lead frame or a substrate, whatever your package is. In our case, the majority are lead frames. What you'll also see, there was a round, a green diagram. Not only do you need to know this, but you also need to know which is the good die and which is the bad die, right? So you'll run a testing, a probing on your wafer. It'll tell you these are the good ones, these are the bad ones. Avoid these, and you can segregate them based on performance. So you have a wafer map. The wafer map has to read exactly what's on the die, what's on the wafer, and you have to make sure that the right die goes onto the right device. So what are some considerations? There's generally three types that we use in discretes, which is eutectic, soft solder, and sinter paste. So eutectic bond, anyone knows what eutectic process is or eutectic bond? It's generally an alloy, right, where the material can go from liquid to solid and solid to liquid with a very short energy. So how does this work? If you have solid to liquid very quickly, you can make that die strength really hard, right? With a certain temperature, you can make it liquid and cool it back very quickly, and that will make sure your bond is strong. Soft solder is solder that we use at EMS, and a sinter paste. This is a new product that's come out, especially for high power and high current and high current devices. If any of you have seen snow, when you pack snow, you get that feeling which, you know, it's crushed and suddenly it becomes solid. That's what sintering is. This is a new method that's being used. What are some other things? The reflow profile. If there is a temperature cycle, the temperature cycle has to be governed very precisely so that you cool it to a place where it can have adhesion and then get solidified right away. Then you have a fillet height and bond line thickness. This is how much solder to put. Why is this important? I'm sure in the second session you'll learn about the coefficient of thermal expansion, right? What is that? Metal, silicon, solder, they all have different coefficients of thermal expansion. What does that mean? That means that you need to have a shock absorber in the middle. Otherwise, they will pull at each other at different temperatures and you will have a die shear problem. So the solder, how much solder to put so that you can kind of bridge the gap between the thermal expansion between the different metals and the die. That's important. All of this is to regulate your bond strength. We want it to be strong enough. And then the other one is ejector needle. So how does the die get lifted? This is the wafer. A die pops the die up and you pick it up. One of the considerations is if you put too much pressure, you might crack the die from beneath. Some small parameters, and again, if you look, what are the key considerations? Material selection is important, because if you don't have the right thermal and mechanical connectivity, conductivity between your lead frame and your die, you will have die shearing. There will be stresses that will cause it to break or perform poorly. Also important for thermal, you have to manage the thermal conductivity so that if there's any heat being generated when the device is in use, it can dissipate easily. Other things are avoiding die tilt and rotation. This is an equipment issue. You need to make sure your equipment is perfectly aligned. You need to avoid die cracking, and then of course, after your die is put, if you guys have ever tried to put a screen protector on a phone, you know there are air bubbles. If there are air bubbles, air is an insulator which will cause fractures in your conductivity. Please. The die is a silicon die. Right. Right. So we use silicon and silicon carbide, but there's gallium nitride, there's a gallium arsenide, and a whole bunch, but silicon is the most popular. We ran a wafer fab. We moved those processes out to some foundries now. So a lot of the processes are still our own. Right. So this is now the wire bonding. This is a simple wire bonding, and here you'll see a clip bonding. On the clip bonding, you'll see there's an arm that picks up a bunch of clips. There are small metal pieces and puts the metal pieces instead of a wire. Can anyone tell me why you would use a metal piece instead of a wire? Anybody? Sorry? The biggest reason is your current carrying capacity. What does that mean? If you have a very thin wire, how much current will it carry? Right? If you want to push higher power through something, what do you need? A thicker wire. I mean, we all know this intuitively, right? Patli tar, utna hi chalega. The thicker the wire, the more power and current it can handle. And if you have a piece of metal, it does better than a wire, right? Okay, so there are a few types of parameters now. There's a wedge bonding, generally for aluminum wires. There's ball bonding, generally for copper or for gold wires. Ribbon bonding is now for aluminum wire. It's a ribbon instead of a wire. It's much thicker, has a much higher current carrying capacity. And of course, clip bonding is where you're putting a metal piece on top. The bonding material, the diameter, all of this is important. You need to know your device, what your device specifications are, and choose the correct corresponding material. If you don't have one wire, you may have 5, right? Because a single wire may not be able to carry all the current, so you disperse it around 5 wires. This type of engineering work, R&D work, has to be done after you know your device specifications, your device parameters, max current, max voltage threshold, etc., etc., etc. So you have to work together with the end product, and this selection becomes important. Further, when you're talking about bonding, there's a loop height that's critical. Why is the loop height critical? You have to ensure that there's sufficient space in the package so that it doesn't touch anything else. Now, you need, what are the key considerations? The bond strength is very critical. Why is it critical? In the next stage, you'll see we do some molding, where we push in some molding compound through a transfer process. If the bond strength is not good enough, what will happen? The wire will get swept away. Just imagine a flood and something gets swept away if it doesn't have a good strength to the ground, right? So we do a hook pull test. So in every piece that we in every lot that we manufacture, a few pieces will be done, and we'll actually pull the wire to see at what strength it breaks. Very critical parameter, right? So you have to avoid wire breakage, lift off, bond tails. You'll have a very small bond pad. You have to make sure that the bond is not trailing onto an active part of the region. And then, of course, controlling the loop height to meet the package requirements. This is encapsulation. In encapsulation, what you'll see is you have a lead frame which has the die, which has the wire bonding, and then you put it in a molding press. And the molding press pushes through a plastic encapsulation, right? If you see the black stuff, that's all an epoxy molding compound. The selection of that's also critical. I'll walk you through that. But sometimes instead of plastic, you also have glass and you also have metal. How many of you guys have used metal semiconductors? You see them primarily in aerospace and defense, which are hermetically sealed, or you see them in what used to be old amplifiers and radios. There used to be a round metal package. I'm sure many of you would have seen that. So what's important in encapsulation? The viscosity of the mold. When you press it through, it flows. What's the viscosity? How smoothly it flows? Are there air bubbles? Should there be air bubbles? How do you control that? Through pressure and temperature. Again, there will be a curing time where you have to give it heat. You have to cure it right after so that it is strong and it doesn't break. And of course, you have to avoid any warpage. When you're doing heating and cooling, you have to make sure there's no warpage to either your die or your entire device. Some key considerations are resin bleed, flash formation, wire sweep. Like I mentioned, it sweeps the wire. Okay. Uniform distribution. It has to cover all the edges of the package without leaving some underfill. This is another very important one, especially for automotive. MSL1 is a moisture sensitivity level. Most plastics have some amount of moisture that can go through. Now let's imagine we're in a car. It's a product that goes into a car or a car charger or something. Can you afford for it to not be in the rain? You can't create a car that cannot handle the rain, right? Same way you can't create a car that can't handle some flooding, as we've seen in, when the rains come, there's water that comes into a certain level. So you have to manage all this sort of stuff. So this is what an MSL1 compound means, the moisture sensitivity level. You can handle it up to 85 to 100% of humidity. Generally, all the testing goes at a 85% relative humidity. So you have to make sure that all this is clear, and of course stability and rigidity after that. Post this, you do a lead finish. A lead finish basically is, this is a bare copper, but I'm sure all the devices you've seen are silver color because they're tin plated. Why do you have a tin plating? So that you can solder it, right? In your EMS lines, you need to solder the product. For that, you need tin. So post the lead finish, you have to clean it and cover the copper with tin. So here are some critical parameters: the thickness of the plating layer, the adhesion of the plating, resistivity to corrosion, and how easily it can be soldered. And again, there's a huge process where you have to control the time, the temperature, the current density. Is it going to get contaminated, oxidized? Is the plating uniform? If it's not uniform, what will happen when you're sitting a component on a board and it's not uniform, you'll have a tilt and you lose contact on one of the legs, right? Can you imagine you have an MCU with say 64 leads and there's a slight difference in heights and suddenly some of them just, you can't solder them. So you have to make sure that you can have uniform plating thickness. Increasingly, and this goes back to the previous session, environmental compliance is becoming important, especially if you're selling to global customers. Roche, REACH, Prop 65, these are all environmental norms that you need to meet in order to sell internationally. So the use of new chemicals, making sure you're experimenting with chemicals that are greener, that are more environmental friendly. If you want to beat this, you may have to change all of this and redo your entire process, right? Chemicals are different. The curing time will be different. The process time will be different. The bath time will be different. So after that, you get to the testing. In testing, you generally have a high-speed tester, so it will take all the devices in, and this is where the test head is. Each device will be 100% tested. In this industry, defect rates are not accepted. You have to be almost perfect or as close to perfect as possible. The consumer has a very, very low tolerance for defects. So you have to do 100% testing. Now, testing again is a very critical aspect. You know the device you're trying to make, the target device. You have to make sure that your tests measure all the possible parameters. But at the same time, if you measure everything, you lose throughput. Why will you lose throughput? Takes time. If you're doing 2 tests versus 15 tests, it will take time. So what does that mean? Your process is slow. The number of units you can do per hour is slow. And what eventually happens, your price goes up, your ability to compete goes down, and eventually you lose market share. So there's a very there's a trade-off at every step of every parameter here, whether it's a cost, time, quality constraint. Some parameter is always at a trade-off, and our job as manufacturers is to make sure we can balance all of these things perfectly so that we can provide our customers with wonderful products that they value. So the equipment calibration is super important. Process throughput and yield analysis, if you are having rejections, why, how do you analyze them, what do you have to do to fix those and rectify those. You have to do both functional tests, which check for logical operations, and electrical parameter tests. Then you've got your marking. Marking is fairly simple. Generally it's a laser marking, but in some places you have inked mark also, especially in the metal devices. You have to make sure there's clarity, resolution, and labeling norms for traceability get very important here. We know companies that have 2D barcodes on every device that they produce. The industry is reaching that level where every single device that you produce will be 2D barcoded, so you can backward trace any product and any problem. This is where the industry is going. So we talk about process, but there's also a whole other section of quality processes, documentation, traceability, design for manufacturing that's going on parallelly. So in the marking, etc., 2D marking is now becoming an important parameter so that we can trace every single device and what lot code and what batch code and what date code and which plant and which unit and who was the operator working on it. It's reaching that level. Then you hit the packing. For packing, generally what we look at is either you get them in the form of reels, in tubes, or some products are sold in tape and ammo, which is another type of packing. Here again, what we need to do in this is make sure that this is the most usable form factor for the EMS companies. So this needs to be working with them. So this you'll have a few parameters that are important. ESD is the biggest one. You cannot destroy the device. Who knows what ESD is? Electrostatic discharge, right? we're all aware of ESD? ESD will destroy devices, especially if it's a sensitive device like a MOSFET. Any static charge will destroy your device. So everything here, especially in the packing, has to be ESD sensitive. And of course, it's a given that all the processes are done in ESD controlled areas. As I'd mentioned, traceability is super important, and we're all doing this so that the EMS guys can do this as fast as possible. The last step is reliability. What does reliability do? Endurance, correct, that's the right word, endurance. I can only test what I have today, but if I'm producing a new product, I have to guarantee that it will work for X number of hours, right? X number of cycles. Do I have X number of cycles before I can wait? Say I want it to run for at least 10 years. Do I have 10 years to wait? You don't have 10 years. So you have to do reliability in the sense you stress test everything, put it into the worst conditions possible and see if it still works. So some of the key processes here are determined by the actual industry. So AEC is by the automotive industry. It's the Automotive Electronics Council. They have their own flow that for an automotive grade product that is safe to use in an automobile, it must be AECQ 101 compliant, right? So they have their own reliability flow. JAN is for the military. MIL is also for MIL 750, the military standard. All your Bell, HAL, etc., they all use products which have accelerated testing to make sure the products are running perfectly. You cannot get a product and put it into space or into an airplane and say, okay, oh, we'll repair it later. That's not a possibility. You have to ensure that it's working perfectly for their stipulated number of hours, for their stipulated use case, because there is no repairing once it's in space. So what are some of these things? Temperature cycling. Temperature cycling takes the product, puts it into a chamber, and the chamber goes from -65 to +150 degrees every 2 minutes. -65 plus 150, -65 plus 150, -65. And you do it for up to 1,000 cycles. 1,000 cycles is 2.5 months. Can you imagine? 2.5 months of just this. If your device survives that, you're good. But it has to survive that. High humidity, high temperature. This will take your device at 85 degree temperature, 85 degree relative humidity, basically a steam pressurized box. And it will pass current through it and it should survive. Highly accelerated stress test. It takes you to 150 degrees with high humidity. There's a whole bunch of tests that ensure that your product can survive, because you can't have something that doesn't work if it's being transported in an airplane in the cargo hold. What's the temperature? Do you think the temperature in the cargo hold of an airplane is controlled? No. But your device and your electronics need to survive. So this is why you need all these things. And you need to really stress it. A lot of time and effort goes into this area. And here, the reasons you need to simulate real world operations and the operating conditions. It also helps identify any failures early on. So any new products you're developing, stress them. If they survive, you know you're good. If they don't, go back to the drawing board, improve, and the cycle repeats. And then of course, this is for aerospace, automotive, defense, they have their own cycles. So if I was to summarize, this is a very simple summary of what we guys do. The dicing processes, the die bonding process, the dicing 6-inch, 8-inch, 12-inch, including silicon, silicon carbide, and glass wafers. Die bonding would be your Tech-Tick, soft solder, sinter paste with silver sinter. Now we're adding copper sinter. This is a month old already that new technologies come in. Encapsulation, which is the molding compound, which is either a green compound or a MSL1 compound. And this is the wire bonding, which you could do copper through thermosonic wall bonding, aluminium, up to 20 mils, ribbon bonding, copper clip bonding, and of course a DBC bonding, which is another thing which is too complicated to get into in this presentation. Your testing and your reliability. So this is the kind of work that we're doing. This is the kind of work that you would be doing if you get into this industry, whether it's with us or with anyone else who's coming up. There's a whole bunch of technology, learning, know-how, process know-how that you guys need to get to speed with. And these are important things that need to be done. There's only so much that can be taught in schools. The rest of it has to be done on the ground. Oh, quickly. So we guys are expanding. We launched some new lines last year. We launched silicon carbide devices 2 years ago. Now we're already exporting to 7 countries for silicon carbide products. In fact, this week we're getting a new line that's coming in this week. So I'll be going to Mohali at the end of the week to install the new line. The spec scheme, the technology roadmap, I think most of these we can just quickly bypass. This is the silicon carbide products. Yeah. I'm open. I'm here for questions. I know we're slightly short on time. Thank you, sir. I'm open for questions. And if any of you are looking for a career in semiconductors, whether with us or with somebody else, please reach out. I'm available. You can email us. But thank you so much. And I'll take questions now, please.
How is fab different from the discrete cell? Why isn't that fab industry require a huge investment?
So the fab process, I think Ashwini ji is a much better person to talk about. But essentially, there are two. The process of doing a wafer has a much tighter process control. The equipment's much more expensive, and it's a different process altogether. You're looking at etching, lithography, your furnaces, etc. That's a complete different. What do you call it? It's a completely different type of process. It's more with chemicals, with hazardous products. And it can be done, but it's extremely expensive because if you want yields and you want to be cost competitive, the larger you are, the better. So the semi industry in general has a very simple rule of thumb. Capex is high, and when capex is high, you want to distribute the capex on as many units as possible, right? So you work on marginal costing. When your capex is high, you are incentivized to build as large as possible so you can serve as wide a market as possible. So you don't need to spend billions of dollars, but you will not be cost competitive unless you do. We'll get there, but first we need packaging. Otherwise, you build a wafer fab, where will the fab product go? Has to go somewhere. As far as I know, so far it's us. I wouldn't say monopoly because it's a free trade product. There's no import barrier, no restriction on this product. It's under ITA 1, so it's actually open to the entire world to compete. You have to compete on your merits. It's just as is. I mean, that's how the market structure is. Once we get packaging in the country, I'm sure we'll build our fabs very soon.
The government is actually taking a holistic approach. You are going to get. It is actually driving the creation of the entire ecosystem. So a day will come where I'm sure Prithvi will actually be getting his silicon carbide wafers here from India. Okay, and either he's going to be making it also, or he'll be buying it from an Indian vendor.
So we're already running some tests with SCL to localize some of our wafers already. So we used to run the fab, so we moved some process technology to SCL, and hopefully we'll have some success there very soon.
And they have a strategic advantage there. SCL and CDIR, they are just one wall difference. So,
right. Please.
Yeah, I have a question. Where do you get your current wafers from?
So as I mentioned, we ran our own fab. So we took that process and we shared it with a bunch of foundries around the world. They are primarily in the East. The West is too expensive. Between Taiwan, China, Korea, Singapore, Hong Kong. Depends on the product. Some guys are good at diodes, some guys are good at MOSFETs, some guys are good at TVS, some guys are good at voltage regulators. Everyone has their specialization. We don't. We believe blade dicing is actually a lot more accurate, because with laser you're adding energy again, and that energy has a chance to warp the die. Any other questions, guys? Okay, I'm around if you guys are feeling this is too large a room. So I'm around. Thank you so much, and a real pleasure to be here. And I'm looking forward to seeing all of you guys in the industry, and seeing your faces over the next few years in different sessions like this and in other industry meets. Thank you so much.
Rashika around? Rashika, so the back. LC number. Okay, Prithvi, Rashka has something for you, but I think she'll take a few minutes. We'll do the honors just on the line. No, no formalities. Really appreciate your session. The one good thing about his session is it's actually covering a part of what I was to cover in the evening. So you're getting a very good view of the packaging, dicing and the packaging industry from a practitioner. There's no substitute to it. Really appreciate your taking time out, Prithvi. Uh, uh, on behalf of the entire group and my own, uh, heartfelt grant for making this happen. If we can get the uh, screen up. So can I ask you one thing? Again, I have some chalks. Uh, what are the hazards of electricity? Shock, fire, anything else? Okay, that's an outcome, but for an individual, shock, fire, what's that? Burns. Okay, deaths. Okay, yeah. Okay, electrocution. Okay, so uh, you can remember it simply. Be safe when you're handling electricity, because B is burns, E is electrocution, S is shocks, or it can be other secondary hazards. Okay, A is arc, flash. Okay, when the dielectric, the air dielectric breaks down and you have a major explosion, that's arc flash. Okay, F is fires. Okay, and E is explosion. You can have explosions also. Okay, so that's the simplest way to remember it. I will try and spare you the full 40 slide deck. I'll try and cover some of the key ones right now. Just bear with me. Okay, electric hazards in semiconductor thing. This has some slides from me, some by Professor Ajay Agarwal, who's a subject matter expert from IIT Jodhpur. I'm actually going to just cover the key message. We have done this. There are major processes in semiconductor, wafer fab product and packaging. They are all going to be using electricity, and there can be hazards on the tool, in the wiring to the tool, in the control panels that are feeding the power to the tools. So you have to take care. Sometimes the energy can be very. It's one of the most latent energy visible in a invisible in any factory operation. It's a real hazard, and it can create disasters like this. It can damage. It can cause fatalities, and it can also create major damages. For the factories. So try and be safe. I've already covered this. The hazards that are there, let me touch on the key elements of it. Okay. So let me touch on the key elements of it. If you take a look at the body's threshold for a shock, up to 5 milliampere, you're somewhat safe, but around 5 milliampere, you will feel the first major tingle. Okay, as you raise the current levels, you are actually going to cross into a dangerous threshold. At around 30 milliamps, there can be respiratory paralysis. It can cause death. 75 milliampere, you will have your heart fibrillation thresholds. Okay, by 250 milliamperes and beyond, you will see heart stopping, and beyond that, organs burning. So electricity is a real danger. Okay, in electricity, remember, a lot of times voltage is seen as a cause of concern. The real threat is the current. Okay, so while voltage matters, current is the
Electricity
real
is
threat.
a phenomenal form of energy, and it's perfectly safe when
Wow.
used correctly.
Okay. Okay, I'll just skip this. And I do want to share the duration of the exposure is really critical. The path to the body is really critical. So a 60 milliampere for 30 millisecond may not cause severe injury, but 60 milliampere for 2 seconds can be fatal. Okay, the path that the current takes through the body, this is going through the heart, risky. This is going through the body, lower body, not so much of an issue. You really have to see and plan for your movements when you are actually working with electricity. If you actually take a look at the frequency of the current at small frequencies, yeah, there is a risk, but people have survived 40,000 volt at 1 million hertz. I didn't know this. This is from Dr. Ajay's notes, but that is actually the reality. At the voltage, at the frequency levels we have in the industry, 60 hertz AC is a risky proposition to work with. So you need to exercise all the care when you're handling the normal electricity and normal devices. Some of the things that are there: failures of electric equipment, damages of installations, working with poorly maintained equipment, selecting wrong tools, working with live power, okay, wrong practices, unauthorized working. These are all real dangers in causing electric shocks. Electric burns, direct and indirect. Okay, in direct, you have a live current passing through your body. In indirect, it is actually an indirect, you will be exposed to radiant heat from arc flashes. That also can be so intense that it can be damaging. It can be fatal. Okay, these are the sort of electric burns, some photographs. Gross, so I will not spend time on it. Key message: you have to exercise care. Understand that if you're working with electricity, you need to make sure that everything that is there in the electric system, the cables, the equipment, the labeling, it is all appropriate. I'll be showing you a video on arc flash shortly. It is a real danger, especially when you're working with very high voltages. You may need to make sure that appropriate processes are taking place. I would rather take you through a video at this point of time than spend time on a slide. You have to have labelings which define the energy levels associated with a particular electrical site. These are done by a specialist who calculate the amount of energy that would get released if there was an arc flash at that point of time. That calculation actually dictates the PPE or the arc flash suit which would be worn by the worker there when he is working on any maintenance work relating to that particular electric panel. Okay, typically you have an energy of 1.2 calories per centimeter square, after which that's the place where you have a secondary burn. Your entire strategy in managing arc flash is to define areas where people's entry is controlled, and if they are entering beyond that limited arc flash boundary, they have to start wearing the relevant PPEs to get into that closer to that equipment. So again, we'll show you that in the video, so I won't spend time on it. Let me skip this. Electric fires are a key exposure. You have seen things like this, I'm sure, if not on the in real life, at least in the videos. You just have to make sure that you're not overloading the system, that your cabling is right. Okay, if you are going to work with electricity, take off all metal parts, including rings, necklaces. Make sure there is no water, no moisture on your skin, on the tools that you're working with. There can be secondary effects. If you're working on at a height, the electric shock can cause you to fall. And as Gauravi said, that's a job hazard falling from a height is a job hazard. Okay, so you need to plan for that. Use the right ladders to actually access electric points. How do you increase worker safety? You do a job hazard analysis, provide the right training, prioritize the PPE and the worker safety norms. They will make a lot of difference. Uh, Prevent overloading, installation failures by regular inspection and weeding out anything that is damaged. Pressure contact failures, conductor fractures. Okay. In case there is a fire, electric fire, can you throw water on it? You can't. Okay. So the fire extinguishers for the electric fire safety, they will be powder based. Okay. They will be based on maybe there might be sand buckets kept at some of the facilities. So you actually look at controlling. You shut off the mains the moment there is an electric fire. Keep the flammable materials in special containers. Check the apparatus regularly. I don't know how frequently these are kept, but if you see those yellow tags, they will mark when it was last inspected. Okay, and if it is there is any deviation found in that inspection, that fire extinguisher has to be replaced. Okay, you de-energize the electric system before you actually approach it. Okay, that is again very critical. The control of hazardous energy is a big thing. You need to have the right PPEs. Let me try and explain what I mean by it. I have at Electronics Sector Skill Council, I actually have been to some sites where they do trainings on to electricians, and I pointed out the one site I went to had actually gloves which were normal gardener's rubber gloves. Okay, that is not appropriate for an electric safety application. Okay, these are examples of electric safety gloves. They have thickness, they have specifications. Depending on what site you are working on, you will have to match the glove to that particular site. Before you use it, okay, you have to test periodically if these are maintaining their integrity. Okay, that means you will actually treat it like a balloon, seal it, check for air leaks. Visual inspections and checking for air leaks. These are up to 1000 volts. These are rated for 1000 volts. There are others. I have got another as a sample here. This is for 33,000 volts. So depending on what you're going to use, you have different gloves. You have to make sure, depending on an application, you have the right PPE there, and the PPE is maintaining the integrity for which it is meant for. You also have to actually do what is called a LOTO exercise, a lockout tagout exercise. So this is a LOTO kit bag. It costs next to nothing. Okay, about a couple of thousand rupees, and I'm having a whole lot of the LOTO components in it, which include not just electric safety, but they include a few other devices. These are all circuit breaker locks that are there. Now I can do it. So this is a circuit breaker lock. Plug it in, lock it into a circuit breaker, and put a lock in it. You have locks also provided in it. Okay, these are interesting locks. There are different color locks. Okay, in a typical electric installation, even at your residence, what happens if an electrician comes? He will shut off the main panel, go and work in the house. Now what if somebody came and said, oh, mera pankha nahi chal raha, let me turn on that particular circuit, if he turns it on, that poor guy might get a fatal shock. How do you prevent it? You prevent it by actually locking it up. He puts this clip up, locks it up. Now nobody else other than the person who has this key to that lock can turn it on. Now let us say that there are multiple people working on a site. Okay, let's say there are multiple people working on a site. You have this hasp claw. Okay, it has multiple holes. In each of these holes, multiple people can put their lock. Okay, so only when everyone who has completed his work has taken off their locks can that circuit be opened. So lockout tagout is one fundamental admin process to make sure that you are working safely when you are working with, you know, latent and hazardous energies. So what you do is, there are multiple steps in it that are defined. You can look at it in Google, but the essence of it is, you first assess where you're going to be, when you are going to work, what are you going to work on for your hazard control. You will make an announcement to all people concerned that I'm going to do a lockout tagout exercise. I'm going to have a machine down. I'm going to be working on it from this date, this time to this time. Okay, you will actually perform a lockout and a tagout. Then you will have a buddy with you with whom you are going to do a qualified verification that the system that you have locked out and tagged out is actually de-energized. Okay, once you know that it is de-energized, you go ahead and start working on it, and then repeat the process in reverse to come back out of that particular condition. Now you can have all sort of kits available depending on the sort of site that is there. For example, here's one. This is a simple class. You can lock it on a gas cylinder. Okay, I haven't seen it in ISC, but you can lock it on your gas flow pipes. You can actually prevent anybody from opening a gas valve if you are shutting it off while working on a chamber. So you must actually look at all these procedures for controlling the hazardous energy. You must make sure that whatever equipment you have is fully functional. Okay, and that's it. One fundamental which is there is, all equipment, it should be well grounded. Okay, if you are working with motors, it should have a fuse. Its ventilating duct should not be closed. If there is a commutation type motor, the bush area should be enclosed to avoid damage by sparks. These are general points. Earthing is mandatory. Ground fault current interrupters are to be deployed judiciously. De-energize with LOTO, very critical, and use appropriate PPEs. Fundamentals, but repeating it again. Plan appropriate PPEs. At applied site, you think these are all esoteric stuff, but at applied site, I have seen the fiberglass hook. If there is anybody who is exposed, you don't have to go and remove him, shut off the electricity, and even then you can't touch him because you don't know if the system is totally de-energized. So you will use a hook to separate him from the live wire. Okay, you need to have the fire extinguishers, the right fire extinguishers for managing your electric fires. If you are looking at equipment, there are times when there are rivet points that are given where test probes can be put in to check out the functionalities. You should not use your own homemade wire going into those points. There will be specific inserts that will be provided by the manufacturer. Use that only. Do not try and take a shortcut for accessing that. If you actually look at how you are holding the tools, there are good practices. Which one do you think is the right way to hold the tool? There you are. I won't repeat it, but you can see which is the right one. That is the one on the left. Okay, interlocks, shields and enclosures. Again, there are different types of interlocks. Respect them. They are put there for a purpose. Lockout, tagout. I've shown you some. You have got a feel of it. The hasps, multiple people have put up their locks. Typically, they are of different colors. Okay, so each one knows exactly what lock he has given. Okay, you can lock different devices out and make sure that while you're working on that particular panel, there is no one else who's going to play with it. What is wrong with this photo? Rakeshji again? Okay. You are absolutely right. Okay. Uh, you're absolutely right. So, gentleman on the left has not won all the PPE. Okay. He has put on a hard hat. He is working with it. But then, because of the panel, I don't know. Here, there is clearly an arc flash label put up. He is wearing a PPE suit, eye cover, electric gloves, hard hat. He is properly geared. Okay, so these are things that one has to remember. Be safe, and please go ahead. We'll break for lunch right now. My suggestion is it's 13:12 right now. If you can come back at around 13:55, I'll take 10 minutes to show you a supporting video, and then we'll get into the next session. And Rakeshji, I have your chalk here. All the notes will be available, that's not an issue. Sir, एक second. Getting all the slides from the other presenters as well. I can't comment on Prithvi's slides. Okay, we can ask him for it. But all the SME slides are available.
the arc flash boundary is to limit the potential burn injury of an unprotected worker to the onset of a second-degree burn. A second-degree burn is painful, but it's easily treatable and usually causes no permanent damage. Workers may not cross the arc flash boundary unless they are wearing the appropriate arc-rated clothing and protective equipment. An incident energy analysis is one method that can be used to determine the arc flash boundary distance. This is a detailed calculation based on the specific design of the electrical system and equipment. Two critical factors used in an incident energy analysis are the maximum amount of short-circuit current or fault current available to the equipment and the speed of the system's overcurrent protection. This information can be used to determine the incident energy level at any specific distance from a potential arc source. For many pieces of electrical equipment, an incident energy analysis has been performed and the arc flash boundary distance is displayed on an informational label. For common types of electrical systems and equipment, the arc flash boundary has been calculated and may be looked up in reference tables published by the Controlling Regulatory Authority on Safe Electrical Work Practices. Using these types of reference tables makes it easier for electrical workers to determine the appropriate arc flash boundary distance. Before using these types of tables, you must understand that the calculations are based on very specific fault current and fault clearing times. If your equipment doesn't match the specifications noted in the table, then an incident energy analysis must be performed in order to determine the arc flash boundary distance. The intense heat of an arc flash can cause normal clothing to burst into flames, resulting in severe and often fatal burns to the arc flash victim. For this reason, our organization provides electrical workers with arc-rated clothing and protective equipment designed to withstand both the intense heat and force of an arc blast without bursting into flames or breaking open. Arc-rated clothing and protective equipment must be selected to meet or exceed the predicted incident energy level of a potential arc flash at the working distance of the task being performed. The working distance is the distance of a worker's face and chest area from a potential arc source while performing a specific task. One method used to determine the appropriate arc flash protection for a given job is to perform an incident energy analysis to determine the incident energy level at the working distance. Once the incident energy level is determined, appropriate arc flash protection can be selected to meet or exceed the expected amount of thermal energy. For common tasks performed on common electrical systems, these calculations have been performed, and the appropriate arc flash protection is listed in a reference table published by the Controlling Regulatory Authority on Safe Electrical Work Practices. Once again, it's crucial that you understand that these reference tables are based on the specific short-circuit current, fault clearing time, and working distance noted in the tables. If your intended task or equipment does not match these specifications, you cannot use these tables to determine the appropriate arc flash protection. For many pieces of electrical equipment, an incident energy analysis has been performed, and the appropriate arc flash protection is displayed on an informational label. There are 4 PPE categories of arc flash protection, ranging from Category 1 to Category 4, with Category 4 being the highest level of protection. PPE Category 1 requires a worker to wear arc-rated clothing of at least 4 calories per square centimeter, a voltage-rated hard hat, and an arc-rated face shield or arc-rated flash suit hood. PPE Category 2 requires a worker to wear arc-rated clothing of at least 8 calories per square centimeter, a voltage-rated hard hat, and an arc-rated face shield in combination with an arc-rated balaclava. An arc-rated flash suit hood may be used in place of the face shield and balaclava. PPE Category 3 requires a worker to wear arc-rated clothing of at least 25 calories per square centimeter and an arc-rated flash suit hood. PPE Category 4 requires a worker to wear arc-rated clothing of at least 40 calories per square centimeter and an arc-rated flash suit hood. Electrical workers are also required to wear safety glasses, earplugs, proper footwear, and arc-rated gloves or voltage-rated gloves with leather protectors. There are some tasks in which an arc flash hazard is not present and do not require arc-rated PPE. When this is the case, electrical workers may wear long sleeves and long pants made from non-melting fibers, such as 100% cotton or wool. Of course, the best way for electrical workers to protect themselves from shock and arc flash hazards is to create an electrically safe condition. This must always be the first choice for electrical workers. An electrically safe condition is defined as a state in which an electrical conductor or circuit has been disconnected from energized parts, locked and tagged in accordance to established standards, tested to ensure the absence of voltage, and grounded if determined necessary. An electrically safe condition is created by first identifying all possible sources of electrical energy to the equipment. Any active loads must be disconnected, and then the disconnecting device for each source of electrical supply must be open. If possible, visually verify that all blades of disconnecting devices are fully open or that draw-out type circuit breakers are withdrawn to the fully disconnected position. Company-approved lock and tag should then be applied to the open disconnecting devices in accordance with our organization's lockout-tagout procedures. Finally, and most importantly, testing must be done to verify there is an absence of voltage and protective grounds installed when necessary. The test instrument used to determine an absence of voltage must be verified to be working properly by measuring a known voltage source immediately before voltage testing and again immediately afterwards. The equipment must be considered energized until you have verified the existence of an electrically safe working condition. This includes establishing approach boundaries and using properly insulated tools, as well as wearing voltage-rated shock protection and appropriate arc flash protection. Once the existence of an electrically safe working condition has been verified, shock and arc flash protection are no longer necessary and can be removed. Other workers who are not qualified electrical workers may then enter the area to perform work as needed. In this program, we have provided an overview of our electrical safety program as it relates to arc flash protection and safe electrical work practices. Make it a point to always follow these practices to prevent being injured by the dual hazards of electricity. After all, preventing injuries is the point of our safety and health program, which is why you must make it a point to be safe.
So as you can see, arc flash, technician is a very specialized role, and in our country, actually, there are a number of, places where you can take trainings relating to it, because we have a very well-established power sector in the country. The best place to take it in the country is in Bangalore, and that is CENTRei Bangalore. Okay. But there are others. You have Hitachi Center in Baroda. L&T has a facility in Bombay, and I'm sure there will be quite a few others in the power sector that we'll get to know of as we engage. So really speaking, when we take semiconductor manufacturing training, what was given by the JJ committee, the 17 odd IITs and ISCs as the provider of training. When you start drilling into these specific roles, you will get all the resources that are available here that we can leverage. Vacuum training that we are doing tomorrow, a part of it, IIT Tirupati, Professor Rao is of course a fountainhead for vacuum technology trainings, but it's also available at a facility in Bhopal, in one of the DSR labs, quite a few other places you can get it. I'm sure ISC will be having that competence to take that up. They do the ultra high vacuum for semiconductors day in and day out. So we have capacity available to groom our first batch of people comfortably in the country. And if there is an issue, I'm sure the government will pay to take resources out of the country and learn from the best and get that practice here. So much so, I would like to get a practitioner in for the next talk. I would like to call in Sharat Kaulji. Sharat is an industry veteran. He was with ISA. He's going to be our industry speaker talking about semiconductor packaging. I think, Sharat, your audience and your floor.
Good afternoon. Can you hear me? How's everybody today? So Ashwini has asked me to speak a little bit about not much so much about the careers in manufacturing and OSAT, but more about the curriculum. So what we've done is I've divided it into a little bit of a high-level introduction about the opportunity, the need, and the call to action for IISc. Then I have, time permitting, a little bit more detail where we drill into an example of a manufacturing company like CeNSE and the type of how we subdivide our job roles, how we segment it, and then how it relates to the curriculum that we're building and the modules. So this is going to be the flow. Just by a show of hands, how many have heard of CeNSE Technology? Okay. And how many have heard of the PLI scheme and the India Semiconductor Mission? Okay, not that many. So everybody who hasn't raised their hand, you have to Google Indian Semiconductor Mission and Product Linked Incentive Scheme. These have been the game-changing incentives that CeNSE Technology has applied for and been approved for to set up an ATMP, Assembly Test Marking and Packing Facility. So about the opportunity, you must have been heard a lot of the announcements recently. Tata has said that they're going to be setting up a digital fab in Dholera, Gujarat. We've got Tata's also setting up an ATMP OSAT, which is outsourced semiconductor assembly and test. So foundries, startup companies outsource the packaging to companies, to the OSAT companies. An IDM is the one which does the packaging, the design, and the fabrication themselves. When you split up the foundry and the design, we call the packaging portion as OSAT, outsourced semiconductor assembly and test. And OSAT does ATMP, assembly, test, marking, and packing. So Tata is doing a fab, the front-end fab in Dholera, and they're setting up an ATMP like CeNSE, but in Assam. CG Power has partnered with Renesas, and they're setting up an ATMP plant in Sanand, Gujarat. Micron, you would have heard about. They were the first ones who got approved. They're an IDM. They have their own fab. They do their own design, and they're going to be having most likely a captive center for their own memory chips. And then, of course, CeNSE, we got our approval in September of this year. We've purchased the land, and we're going to be having our OSAT facility in Sanand, Gujarat. So we are in the process of looking for the top talent of the country. I'll explain the process which we're following in terms of talent acquisition. Immediately, in the short term, the plant will be ready by probably Q3 or Q4 of 2025. But prior to that, we're going to be setting up a prototype line. So we are actively hiring today. We need around 7 to 8 laterals and around 18 freshers by March or April of this year. And of course, Foxconn and HCL, we haven't heard much about that yet. I think they need a technology partner. And one of the names that's missing on the list is, of course, Adani, which is planning to set up a fab in Maharashtra. So this is the basic phases in which CeNSE is going to be implementing their OSAT project. We're going to be starting with high volume, high yielding, robust, mature technologies. And those technologies are in the form of package types called QFN, quad flat, no leads. And another area which we're going to be focusing on the beginning are TO and SO packages. So gallium nitride devices that we're manufacturing here at CeNSE, silicon carbide devices, high voltage, high band gap devices typically are put in TO and SO packages. The 3-pin leads that you see. The QFN packages can take digital ICs as well as gallium nitride with wire bonding with the lead frame, and then we're also going to be starting with flip chip. So we're going to be taking the QFN packaging, flipping the chip inside, and then having both wire bond as well as flip chip. Does everyone have an idea what flip chip and wire bond is? Basic sense? Okay, fine. So maybe I can. So, yeah, good. So I was talking, these are the wire bonds. You can see here, and the die is facing up. When you flip the die 180 degrees, you don't see the wire bonds, obviously, because you're connecting it to the PCB with bumps. So that's why you don't see any wires. And then that'll be phase one, mainstream examples. And then probably in years 2 and 3, we're going to be getting into more advanced packaging, which is in the area of 2.5D, stacking dies, heterogeneous, and flip chip BGA, finer pitch BGA. And then the ultimate, where the whole industry and the globe is going towards, is something called co-package optics, which is nothing but using optical fiber between chips, and from the chip to the package and board to board. Today we're connecting countries with fiber, but now as we're getting to the more and more bandwidth in the area of AI, the bottlenecks are starting to become at the chip level, at the connector levels now. And so that's going to be coming, and we've already started talks with some of the institutions in India. So the basic requirements for a semiconductor manufacturing job, there's varying. Like Sir was saying, it's a multidisciplinary, chemical, mechanical, electrical, computer science. It's a pyramid approach, and the bulk of our hiring, you could say 50% is going to be the ITI and diploma. Of course, these aren't the ITI and diploma audience here. But of course, the next layer up are going to be the MTech, the BTech, MTechs, and PhDs. Then we have the BTech, MTechs, and PhDs, which are laterals, which means they have work experience. And we have a separate segment altogether for research and development. So in each of these areas, we have further bifurcated them into our need. And this is what a roadmap that we've presented to the government of India when we submitted our application. So you can see year by year, you can see a steady ramp of getting from 300, and we have a little bit of a shift here because our approval came a little bit late. So this has actually been shifted to December. We need 300 people by December of 2025, out of which 150 of those, 50%, are going to be the ITI and diplomas I mentioned. And we have a roadmap, as you can see, by 2029 of having close to 2,000. The industry released a report, Ashwini Sir was part of that, a skilling report where they estimated 85,000 people are needed by 2027. That date is shifting a little bit, but in that 85,000, they've divided it into design and manufacturing. 80% of the jobs are going to be in design, 20% are going to be in manufacturing. In those 20% manufacturing, 10% would be mostly front-end, fab, and 10% would be back-end, packaging. So 10% of 85,000, 8,500. From what we're seeing, that number which they had projected to 27, 28 is actually moving left. In fact, that requirement is going to be sooner than we expected. And we expect that number to be maybe 4x or 5x that requirement. So from the time the report was written in November of 2023 to now, we're already saying that we have beat our expectations, and we're going to need much more talent in the industry to fuel it. And my friends, this is just India. The globe needs exponentially more number of people. So this is not just an Indian opportunity, it's an international. But I'm not saying leave India and go for MNCs and international jobs. I'm saying stay in India. The opportunities are good here. But the opportunities are there at a global level. We are the youngest population on the planet. We'll continue to be the youngest working population until 2070. So at least in my lifetime and maybe your all's lifetime. So this is a typical example of one of our first projects, which is our prototype assembly line, which we're going to be having in Chamarajanagar, Karnataka. It's just south of our main headquarters of CeNSE Technology. And as you can see, we need about 7 laterals. These are experienced people. And then we need freshers across QC, maintenance, production. So 25 people to run it, of which 7 lateral and 18 fresher. This gives you an idea. So this we're hiring immediately. We're making offers for ITI and diploma, and then we're going to put them through hands-on training. Until the prototype line comes, we're looking at IISc, we're looking at CMTI, we're looking at SCL. But those lucky few that get shortlisted who have had packaging training and that have gone through the on-the-job training and this hands-on training will then be deployed at CeNSE Semicon, and they would have the choice to work in Chamarajanagar or in Sanand, Gujarat at the production facility. So this is how I was talking about that main chart. Not only have we shifted by 9 months because our approvals came late, but now we've subdivided it. We have to divide it up by quarter, and we've divided it up by our various departments within the OSAT. So within the OSAT, I already talked about the prototype line, which needs 25 people by the end of the year. And by March, April, I beg your pardon. But the actual production facility, by December end, we're going to need 200 people. Nothing in the first quarter, but then we're going to be rapidly ramping up in Q2, Q3, Q4. Similarly, the bulk of our hiring will be on the production line, the wafer dicing, the die attach, the wire bonders, etc. However, we also have a separate department which is reliability and FA, where we're stressing the device out with temperature, humidity, dust, voltage, current, and you're doing the characteristics and also failure analysis. Similarly, and that's a little much lesser quantity, about 28 people by the end of the year. And then we have something called ATE, which is the automatic test equipment. Once the package is done and it has the lid on it, it has to go through the automatic testers by Advantest and Teradyne. This is a very, very niche skill, and India lacks this, and it's going to be needed in abundance soon. So if you're interested in validation, testing, qualification, then you can look into jobs into AT as well, automatic test equipment. And then we have, already we have 2 PhDs. We're going to be making an offer to a third one, and we have another 2 slots open before the next event year for a total of 5. And then by next year, we'll be increasing dramatically from 300 to 825. Again, I don't want to bore you with all the charts. I'm just trying to share with you how an industry approaches their hiring. That's the whole intention of this. And so what we've done then is we've taken those quarters, and now we've had to actually break them out by levels because we've gotten training curriculum for packaging from AICT. We have a training curriculum from IIT Kanpur. We have a training curriculum from IISc, from IIT Bombay. There's a PDC course running in BITS Pilani, Hyderabad. They're all having different modules serving different needs. So what we did as a team, and actually as a, as you can say, an industry consortium, we are consolidating all of those modules as a superset, and we're pulling out those modules which would be applicable to ITI freshers, diploma, BTech, BTech laterals, and expats. So from January to March, January 27th to March 3rd, we're going to be conducting an online training free of cost, CeNSE, for the state of Gujarat, but it'll be open to the rest of India as well. The shortlisted candidates from that online massive training will be selected for the, I beg your pardon, the best shortlisted students from the theory training, which is online from Jan 27th to March, would be selected for the hands-on training, which would then be further selected for a job placement at CeNSE. I talked about the prototype line, I talked about the production line, I talked about AT and R&D, but of course R&D, our focus is going to be on two main vectors. Our existing line and improving the yield and decreasing the cycle time, getting the yields up to 99.99999%. That means 1 failure out of 1 million. We plan to do 1 billion chips in a year, 60 to 70 lakh chips in a month. You cannot afford to have 1% yield failure. It can't be 98. It can't be 98.9. 99.9999. So the R&D team is going to be maniacally focused. We'll also have segmentations because CeNSE Technology, prior to launching CeNSE Semicon, which I'm a part of, is an Indian leader in SMT, in EMS, where they take the packaged devices and put them on the PCB. So the thought process for CeNSE was to do backwards integration. And CeNSE is a leader in India today for the automotive EV segment, particularly on the battery charging systems. So as you know, the battery charging system voltages, DC voltages are getting higher and higher. Devices like GaN, silicon carbide, IGBT are used in battery systems. And these are all our customers which we're today importing. So we're going to be focusing on 2 main segments, which is the power electronics, and the second main segment is on the high performance computing. CeNSE is also building the Rudra supercomputer for CDAC. So we want to see what we can do to make as much of the motherboard as much indigenous as possible, and CeNSE wants to package those devices and make the next CDAC supercomputer as much indigenous as possible. So 2 segments, high performance computing, which is more on the digital side, very low DC voltages, very low current, but extremely high power consumption. And then on the left side of the equation, you have power devices, which are older technology nodes, much higher DC voltages, and much slower switching frequencies. So they have very, very distinct markets, very distinct applications, and they're all packaged differently. And of course, the R&D team, if you're so inclined, would be working in parallel on advanced packages. I talked about the roadmap 3 years from now where we're looking at co-packaged optics, we're looking at chiplets, we're looking at 3D ICs, stacking with copper pillars, through silicon vias, actually putting vias through the entire wafer and stacking them. This is very advanced technologies, and we're not at a situation where we're getting those 99.999% yields. It's an R&D, but we are absolutely looking at that for the future. So as I mentioned, we've broken out our training plan and our curriculum into diploma and ITI, which are going to be the machine tool operators and the technicians. The graduates, the freshers, BTechs, and MTechs are going to be mostly working on statistical process controls, modeling, automation, managing the shop floor, predictive maintenance, smart factory 4.0, making the machines talk to each other, collecting the data logging, analyzing this vast amounts of data. And then of course the laterals are going to be the ones who are going to be managing the freshers and the teams. And I already talked about the research. So very quickly, how much time do we have left? 5 more minutes, sure, and maybe some questions. This is a very high-level overview of the thought process of those diploma and technician freshers, the criteria that we need at Kane Semicon as a manufacturing company in India. We are going to take these requirements and pull out those necessary modules from all of the curriculums, making sure that A, it falls within the AICT model curriculum guidelines, B, that we align it with the university programs, so they're typically 42 hours in 14 weeks in duration. So that's approximately 3 credit hours in university parlance. When you add on the hands-on training of 15 hours, we hope to establish this as a 3+1 that would be applicable to the college degree or your diploma. We're not there yet because it's still a work in the process, but in January to March, you're not going to get the college credit, but you'll get a certification. But in time, we absolutely expect that this can be as part of the college credit towards your diploma. So this is for, you can see, the diploma and technicians are going to be machine specialists, like Sir was talking about. They will be focused on their machine, the predictive maintenance of that machine, the calibration of that machine, all of the safety aspects of that particular machine. The hands-on training will be on a specific machine of the flow, and I'll share with you the flow chart. As I mentioned, tool-specific. Basic fundamentals we're looking at, Ohm's law, Kirchhoff's law, Newton's laws, the basics. And then we want to build on those basics and see those enthusiastic people in which area of packaging they're most interested in, whether it's automatic test equipment or whether it's on the optical side, on the quality side. They're going to be using tools for like X-ray inspection, SAMs. They would have to be able to, on the floor, quickly be able to categorize any failures. Because as you know, the line has a step-by-step process, and if there's a failure, they should quickly be able to know how to bin it, how to classify it, so that then the failure analysis team can then do the reverse engineering and debug it so the future failure doesn't happen in the future. Of course, statistics I was talking about. We're not expecting you to be a PhD in statistics, but understand Six Sigma, understand the fishbone diagram, understand what it means to do a deviation, regression line, basics. Very important. So anyone interested in this type of industry where you have looking at high volumes of extreme complexity, statistics is a must. And we're going to have different levels of SPC for the different layers. Soft skills, I can't tell you enough. I mean, ability to communicate, ability to write an email, ability to write a beautiful report, being able to communicate the issue in succinct professional format is extremely important. Being able to collaborate with your peers in different countries, different cultures, different languages, being attuned to the latest technologies, to use technology to our advantage in cycle time reduction and yield improvement. And of course, we'll be making these modules available online. And of course, the next would be the engineering freshers, the B-Techs and the M-Techs. This will be a much more in-depth. And they're going to need to know much more on the chemical properties, the various temperature coefficients, melting points of materials, compounds, elements. They'll have to have hands-on experience. They may not be working on the machines on the shop floor. They'll come, but not like stuck to the machine. They'll be more overseeing, but they have to have hands-on experience. So we'll put them through the hands-on training. Again, they should know about the entire flow, not on a specific machine. And of course, again, statistical analysis, design of experiments, failure, on-the-job training, etc. And then, of course, lateral, I don't want to spend too much time. Most of, I think, us here are freshers. But we do have a good requirement of laterals. And it's a tough challenge for companies like ours because India doesn't have fabless chip companies. We don't have manufacturing in here. So where do we get those laterals from unless we get them from abroad? So we end up poaching from one another. That situation needs to change. So we need to have this capability in India. That ecosystem is being built. So that ecosystem is getting built now. And I talked about the PhDs, about 2.5D, 3D packaging, wafer level packaging, co-package optics, design of experiments. This is where the high-end statistics come into the play. The PhDs are going to be the ones who are going to be defining the models and the dashboard for the rest of the company. The PhDs are going to be working with the engineering team to be the buffer between the executive management and the factory floor. They will be creating those charts, which are going to be the communication mechanisms between technical and management. And their role is going to be absolutely critical as we move forward. This is a chart from a market research firm called Yole. I don't expect you to go through all the fine print, but basically what it's communicating here is on the y-axis you have applications. I already talked about HPC. I talked about high power voltage, but there's many other applications. And then on the x-axis, you have the different types of silicon devices: digital, analog, sensors, MEMS, microcontrollers, CPU, GPU, etc. Every package has a specific place and a purpose. Every package has its pros, every package has its cons. You can have high frequency, low frequency, high DC, low DC, high AC, low AC, low power, high power, etc. So for that matter, this matrix does a good job in explaining to you the different types of chips. FC stands for flip chip, system in packages, SIP, etc. And you can read it on QFN, QF, etc. It's all there on the bottom. But this gives you an idea about how vast and how many different types of package across applications, across different IC types there are. And of course, we're going to be setting up a mentor-mentee system. I won't go into too much detail here. We're going to be executing these on stage. Like I mentioned, we're in stage 1 right now. And we're in stage 1 with our razor-sharp focus on March and April to get those 18 freshers onboarded immediately and the 7 laterals. Immediately from March, we're going to be putting them through the hands-on training on the machinery. Then they are going to come to factory, and they're going to get on-the-job training, SMT, and get acclimated with the company, evaluation, and then they're going to be hitting the ground running and contributing. This is the basic process flow. You can go through it. So you get the bare wafer. It has a sticker on the bottom. You have to dice it up into small pieces. Sometimes you actually work on the wafer also, by the way, even before you dice it. Then you have to do the curing of the die. You attach the die to the package. And inside the package, there's a rail, pin outs that connect the die to the bottom of the chip, which goes onto the PCB, the motherboard. So that process where you attach it is used as epoxy. You have to cure it, then you connect the wires for non-flip chip, or you flip the chip over and there's no need for wiring. Again, molding, which is the over casing. There's 2 types of moldings. You can have open cavity for MEMS, for example, and you can have closed cavity in the case of wire bond. Again, molding, laser marking the top putting the logo, putting the part number, putting the lot number, all the data. You mount it, put them in trays or on reels, and it goes to the distributor. So this is the flow that ATMP does in semiconductor back-end manufacturing. So that's all I had, and I would love to open it up for questions with the remaining time we have.
What's the kind of investment we talk about? Say factories that we are setting up, 5, 6 companies are setting up, where they're duplicating the investments, where the government is encouraging duplication. What are the kind of government support is needed?
Sure. So the question was, what was the government support? What is the approximate investment? And why is there duplication? So I'll take them one by one. CeNSE is around a 5,000 crore project to do about 60 lakh parts a month. It's an OSAT. We're focusing on QFN for power modules. And we're also focusing on HPC. Tata's is another OSAT, but they're 21,000 crores. They are going to be getting their wafers from their own 28 nanometer digital fab and packaging it. Their requirements come from Tata Advanced Systems, Tata Defense, Tata Alexi, Tata Electronics. Tata's everywhere, right? They absolutely will be doing it, but they're becoming an IDM. We are a pure play OSAT, so that answers the question. CG Power and Renaissance, they're going to be doing mostly, I think, digital products actually. And then the incentives you were talking about come in multiple ways. The biggest one is the PLI scheme I was talking about. So on a project cost of 5,000 crores, the government gives 50% of that, 2,500 crores. The state government gives another 25%. So 75%, if you're approved, is actually funded on a pari passu method, which means you put 1,000 crores into the account, government will put 1,000, I have to get the numbers right. 1,000 represents 25%. Government should put 2,000 crores. CeNSE should put 1,000, the state should put 1,000. That's how the project comes together. That's one of the schemes. There's also a scheme called EMC 2.0. That's in incentivizing the government to give large parcels of land called electronics manufacturing clusters. And in these clusters, the underground plumbing, the OFC cables, the DI water, the supply chain, plug-and-play facilities, so entrepreneurs can set up their manufacturing from day one. So the government has EMC clusters all over the country. You can just Google it. So from your hometown, you see the nearest EMC cluster, and they have plug-and-play facilities where manufacturing can then apply for PLI after that. So then you have very different, so Micron is another example, which is completely independent of what CeNSE is doing. We're not doing memories. Micron will be doing predominantly memories, NAND and DRAMs, right? They're going to be doing HBM 3D stacking. We're not doing that. And I showed you that complicated chart, right? So there's a lot of, there are overlaps, but there's a lot of independent sets also. And there's a place where everything and the volumes are huge. And let me tell you, AI is going to drive the next 50 years. The supply of chips will never be met because the amount of computing that's going to happen, in the way the cars and our vehicles are transforming into basically computers on wheels, it's all going to be driven by semiconductor chips. So in the next decade, you are going to see a market that took 70 years to reach 500 billion. In the next 6 to 7 years, it's going to reach 1 trillion. What's happened in the last 70 years is going to happen in the next 5 to 10 years. It's going to be exploding. Yeah. Next question?
Thank you.
Yes, sir. Okay. CeNSE Technology is a EMS company which does SMT. That means that they get the packaged parts imported, and then they solder the parts on the PCB, and then they test it. Okay, so that applies for all industries. The OSAT, which we're setting up, is backwards integrating and actually packaging the chips now. So instead of the chips coming packaged on trays or reels, they'll be coming in as wafers. Right. So it's totally different. And the HPC question you had is something different. Today, CeNSE Technology is doing the CDAC with their computer. They're doing the SMT, not the packaging. So it uses Intel motherboard. So all the chips get imported, the PCB gets imported, CeNSE assembles it, and we do the end box build, the actual chassis and the racks. So that's what CeNSE Technology does. And by the way, CeNSE is also backwards integrating, and we're also setting up a PCB fab, by the way, as well, as part of our future plans. We good on time? So thank you very much for your time today. Wish you all the very best with your careers and your interest in semiconductors. Okay. Sure. Oh, thank you.
Hello. Uh, Good afternoon, everyone. I am Prashanjit. I am at CeNSE. I think you have had a chance to visit CeNSE. So I work at CeNSE, and I am a part of our packaging effort that goes on in CeNSE. So today I'm going to talk about packaging processes and packaging technologies, how it has evolved, where it is going. And this is primarily a summary of the class that we teach at ISC. So before we start with how we do advanced packaging, what is advanced packaging? Advanced packaging today basically means that how do we interconnect chips to build systems, right? It's not just taking a chip and putting an epoxy mold around it with interconnects, but it is also going to the level where you have the finished wafer to the final system. Every part of that whole process flow is getting affected by how the packaging technology is evolving. And the second point that I want to make before we go into the details, that as you can understand, it's a very, very interdisciplinary area, right? It's heavy on materials, mechanical engineering to understand stresses during packaging, electrical engineering, electrical design and fabrication processes, right? All of these different areas have a role to play, and hence a packaging team very often consists of experts from all these different backgrounds, right? So let's ask the question, what exactly does a package do? What is the function of a package? Why do we have a package, right? So package, this is what one of my friends Subbu says, the main function of the package is to protect and to serve, right? It is to protect the device and to provide the device with certain services so that the device can function in an optimum condition. What are the protection? Mechanical protection. So, it provides mechanical protection from handling, stability, environment. So, it protects the device mechanically. It provides environmental protection from moisture, it provides hermeticity wherever hermetic packaging is required. It protects us from corrosion as well, right? Then there is thermal protection, right? The idea of thermal protection is many devices will be generating a lot of heat, right? How do you take the heat away effectively from the device and sink it to the atmosphere is again a challenge. So, that is also the role of the package. The package is essentially taking the heat, spreading the heat out, sinking it to the atmosphere, and it is trying to reduce the hotspots. So, these different kinds of protections is what a package provides. At the same time, it also serves. What services does it provide to the device? It allows electrical interconnects to the chip. So, basically what it is saying is, if you think about a PCB integrated system today, you have these silicon devices which are lying inside this plastic molded chips, and there are two different chips, right, which are encapsulated within their own epoxy molds, right, or within their own packages. Now, they have to communicate with each other electrically. So, it is the function of the package to make sure that your electrical signals travels from that silicon chip out to the PC board, go to the other package, and then back into that other silicon chip. Now, it is the function of the package to ensure that this signal is getting transmitted reliably. Okay? As the world is moving towards higher and higher bandwidths and higher frequency signals, this becomes a more and more challenging task to make sure that the signal goes from this chip to that chip reliably without losing the fidelity. Okay? So, providing electrical connections so that the signals can transmit between these two chips is the functionality of the package. Deliver power. Okay? Delivering power to the device so that it can function is also a function of the package. Why it is becoming a problem? The problem starts happening, it's different from providing electrical just the signal transmission, because the challenges are different. You need to provide a lot of current to very small area devices, right? And how do you do this when your interconnects themselves are becoming smaller? So, today when you are talking about a few nanometer devices, right, the electrical wiring which is there inside the chip at the lowest levels are also in the similar dimensions, right? Now, think about a power that is to be delivered from outside to a transistor on a silicon device, right? It has to travel through a multiple layers of metals and then finally travel through this very nano wires, right? So, this power delivery itself is becoming a problem. I don't know how many of you have heard about it, but Intel recently talked about power delivery through the back of the chip. Yeah. So they are trying to solve some of these very hard problems of delivering power and signal while your chip is becoming, or your devices are becoming extremely small, chips are becoming extremely large and complex. Okay? And then finally is to provide optimum environment for operation. We will come to this aspect later. So, we will try to remember all these things, what are the functionalities of the package, and then we will try to go from step to step how the technology has evolved and why it has evolved in certain manner. So, before we actually go into the processes, we would like to see some examples, right? This is a high performance board and there are multiple packaging challenges here. Okay? One of the evident packaging challenges is the heat, because your processors are generating a lot of heat. How do you take the heat out, right? Then, as you see, there are multiple layers of memories that are present inside your high performance board, right? Because today, when you do any computational operation, right, there is essentially two types of functions that are happening very roughly, okay? One is you are trying to get data from somewhere, you are operating on that data, and you are then pushing that data back to somewhere else, right? And that has to, all of this has to happen at a very, very high speed, okay? Because very often today, the operation of getting the data in and sending the data out often becomes a bottleneck in this process. So in this case, when we talk about this high performance boards, one of the major challenges is how do you ensure that the processor is always having enough data to process or work with, right? And this is where, again, further discussions we will come back why certain technologies are coming up. So again, if you look at this board, you would see that these, again, some of these inbuilt RAMs which are inside the processor, they go closer to the processor, they are inside. Then here comes the faster version of the RAM, which is temporary but much faster, and then your slower memories come in with. So the capacity keeps on increasing as you go away, and the speed keeps on decreasing as you go away from the processor, right? Then a different challenge comes in when you talk about consumer products, right? This is, I think, from an Apple Watch. This assembling this kind of devices today is extremely difficult, okay? And designing them is also difficult because there are so many different kind of functionalities that are going inside these individual in this small form factor, right? Now, again, we will discuss some of the things that are happening and some of the technologies that have come up to address some of these issues. Then comes biomedical device packaging. Again, here, in addition to reducing the form factor, reducing the power, having good EMI and electrical solutions, biocompatibility is an additional problem, right? And reliability, again, is a very, very big issue, because this is a pacemaker device, I think, and the problem is there is absolutely no space for failure, because a failure means a loss of life, right? So here the packaging problems and the packaging goals are again very different and hard. And finally, packaging of MEMS devices, they also come with their own set of challenges and problems. One of the biggest problems with the MEMS devices is most of the MEMS devices are movable in nature, right? They have structures which move with respect to the frame. When you have moving structure, you are essentially creating cavities inside your devices, and you are trying to put the devices in those cavities where they can function. Now, what is the problem in packaging with cavities? The main challenge comes is that these cavities need to have a very specific environment to operate. Like, if you think about an MEMS oscillator, right? CeNTrei has this product which are MEMS resonators which are replacing quartz devices in many applications. If you look into those CeNTrei oscillators, the oscillators need to be packaged inside a, any guess? What kind of environment? Vacuum environment. They need to be packaged inside a vacuum environment because you don't want the viscous damping from the air to reduce the Q factor of the resonator. Because one of the biggest selling points for MEMS devices is that they have very high Q factors. Q factor essentially takes how much energy it takes to keep the system in oscillation. As your Q factor becomes higher, your energy requirement decreases, and you can have very low power oscillators or resonators at very different frequencies. So then that means that if I am packaging a MEMS oscillator or a resonator, I have to package it inside a vacuum environment, right? Again, those comes with their own inherent problems and challenges. Again, there are other areas. How do you integrate optical devices photonics, how do you integrate it with electronics, how do you do package for RF devices, how do you do it for automotive, fluidic, and etc. Recently I heard a very interesting view from an expert that automotive packaging historically has been a challenge in terms of reliability, because your environments are very harsh. So you try to make devices and package them in a format that it works at very high temperatures, very corrosive environments, etc., etc. But one of what the viewpoint I heard recently is that, see, most of the vehicles are now going towards electrical domain. Now, if you go to electrical domain, some of these challenges actually go away, and your packaging requirements will become much simpler when you think about electrical vehicles in compared to traditional petrol or gas-based vehicles, right? But again, this is a question. But there are so the point I was trying to make is that lot of these requirements are also dynamic, dependent upon how the application area is changing or evolving. Okay. So what is advanced packaging and integration? As I was mentioning today, advanced packaging starts after the wafer has been fabricated inside a fab. Then it gets converted into some kind of package. Then they get assembled on a board with discretes. Now this again has become short circuited with introduction of chiplets, where these ICs are directly again getting integrated on a silicon or a glass substrate, not on a PCB, right? And with discretes, then from there you go to the system. All of this comes under packaging today. And what is happening also is a lot of this demarcation is going away, because once you start talking about chiplets, then the type of facility that you're talking about is at par with fabs today. The level of cleanliness required, the level of tool set required becomes almost as almost similar to a fab today. Okay. Again, how do we look at IC packaging? So let's look at one of the most traditional and way of packaging. The first thing that happens is after a device has, after a wafer has been fabricated, in a wafer we normally tend to fabricate as many devices as possible. That idea is clear to everyone, right? So normally whenever a silicon is processed, wafer is processed, and when we make devices, we try to fit in as many devices as possible. The idea is it parallelizes the process, brings the cost down, and hence makes it a feasible technology, right, and profitable. So the first thing that you want to do is dice. You cut these devices from the wafer into single dies, right, or the single devices are singulated. What are the processes that you can use? Saw dicing. Saw dicing is basically a mechanical saw which cuts through it. Any other technique? Laser dicing is the second technique. Any other? Scribing. Stealth is a laser type of a different type of laser, or more better way of doing dicing using lasers. Plasma etching is another one. We can use the same deep reactive ion etching kind of techniques which are used to manufacture the devices for dicing the devices also. So that after we have diced, then what is done is the chip is attached to a package substrate. This is a substrate made out of plastics, made out of ceramics. And what is the nature of this substrate? It will allow a place for the die to be attached, and it will also provide some electrical leads which will come out of the die, and we will be able to connect electrically to the die sitting inside the package. So there are leads which are coming out. So you see these lead connectors which are shown here, and this is your die where it gets attached. Normally, the standard way of attaching the die is using epoxy. So you will have some kind of epoxy, the die will come and you will attach it at that position. After that, we will make electrical connections between the die and the pads outside. This is very often done with wire bonding techniques, right? So there will be equipment, we will talk about it in another slide later. So there will be an electrical point connected here and then the wire will go and connect here. So these connections will be done. After that, we go into the process of epoxy molding. What is being done is this chip is packaged inside and now an epoxy case is being created around it for the protection. Right? Now, this gives your device. Now, this is again from the side view. There are variations of it, but overall in concept, generally there are these major steps that has to take place. So, the die attach, wire bond, molding or encapsulation. If you have a ceramic package, then you don't do an epoxy molding. You will have a ceramic case and then there will be a glass lid which will be attached onto it. Okay. So, again, there are many, many different kinds of packages which have evolved over time. These are some of the standard types. There are also a lot of non-standard packaging types which are also available, right? But if you think about it, here the whole concept is again the same. We are placing the chip inside so that it provides protection. We are providing a connection to the outside world to allow the power to go in and the signal to go in or come. Okay. All right. So, yeah.
So in the second stage, there is
Yes.
a chip in the center and then there are those wires coming in. Terminals on second stage.
Huh.
So the connections on the chip are at nanometer scale.
No. Pads, the final top pads will be micron scale, tens of microns to hundreds of micron scale.
So what would be the size of those connection wires?
Wires are 100 microns, 50 microns, 75 microns. There are different diameter wires available.
So that connection is happening. What is the process that?
We'll talk about it. So wire bonding, we'll have a slide about it. Okay. So what we'll try to do is we'll try to briefly discuss why certain type of steps are selected for each of these steps. Okay. Okay. So these are some examples. Again, one of the other aspect of packaging is to take heat out of the devices, right? And some devices do not generate that much heat. So if you have a packaging scheme which is like this, right, where you have this die attached pad, you have these leads which form the package substrate, then the chip is attached, wire bond is made, and then you have plastic encapsulant. So if you have a scheme like this is okay for devices where there is not enough heat getting generated. But if your chip is a power device which is going to generate heat, this approach is not good. Why? What is the problem? Because plastics are very poor conductors of heat. What is going to happen is your heat is going to get trapped here and your temperature of the die is going to become very high. All silicon devices have a maximum operating temperature. Beyond that, it will not function. So this is not a good approach. There are other approaches. One approach could be where you have the die connected to the copper sink as close as possible. I'm not going to go into some of these other intermediate materials today, but if we can come up with a technique where the device is directly connected to the heat sinking material, then you would be able to take the heat out most efficiently. So depending upon your application, the reason I wanted to just discuss this slide, and this is not the only solution for thermal packaging. Okay, there are many, many solutions and different solutions depending upon how much heat you are generating, what is the maximum temperature that is possible. The reason I wanted to discuss or show this slide is to impress upon you there is no one single solution. Okay, depending upon your application, depending upon your parameters which bound your operating space for your device, your packaging solution has to serve that purpose, right? And try to serve that purpose at a lower cost if possible. So again, we will not go into this slide, but essentially if I have a device which is generating heat, right? And today we also know where in the device that heat is getting generated, right? So if you think about a gallium nitride device which is sitting on a silicon carbide, it's exactly known from studies and models that which is the region where your heat is getting generated on the device. So if you know where the heat is getting generated on your device, you can come up with a very good model of how much is the expected temperature rise for a given power by doing first a very simple back of the hand calculation, which is assuming a 1D heat transfer, and then using one of the tools which will allow you to do full 3D heat transfer with much more complicated boundary conditions. But this is possible, and that allows you to design the design how you want to package for your high high heat or high heat generating devices. So again, in die attach we just talked about one process like epoxy based die attach, right? We said that you take a die and you have the package substrate and you attach it using epoxy. Under certain conditions, when that attachment is not favorable, again in the case of where you are generating heat, right, and you are trying to take the heat out from the bottom of the chip, right? So suppose you have a substrate which is a metal substrate, and then you put your die onto that metal substrate, and that becomes your back pad through which the heat is going to go out and sink. Then epoxy might become a limiting step, right? Because epoxy has again is a polymer compound which will have a poor thermal conductivity. Today there are epoxies which are available with high thermal conductivity, but still they will not perform as good as something like a silver paste, right? So there are processes which are available to allow you to bond by the device onto the package using direct metal kind of contacts, where you have a silver paste, the chip comes in, and then you go through a vacuum sintering process to get a sintered layer, which is again connecting the chip onto that package substrate, which can allow you for a much efficient heat extraction than compared to the epoxy. Okay. All right. Now this sintering process is happens through a process which is known as transient liquid phase bonding, where you have materials like silver, tin and silver. Silver tin forms an alloy, and that alloy helps you to form the bond, right? Now in this case, why do we call it transient liquid phase bonding? Transient liquid phase bonding. So the idea about transient means happening for some time, liquid phase. So what is happening is, once we put these two things together and heat it, then tin will start melting at 232 degrees C, right? Once tin starts melting, it will start actively forming alloy with silver. So what will happen is you will have growth of tin silver alloys. Now if you look at the tin silver alloys, then their melting temperature is much higher. So what is going to happen is, as your silver is alloying with as your tin is alloying with the silver, it is precipitating out and forming a solid, right? And as the silver keeps on the tin keeps on moving and alloying with the silver, more and more liquid tin is getting converted to silver, getting converted to solid. So after all the free tin has been consumed, you will be left with a solid phase. That's why it is called a transient liquid phase bonding, where the liquid phase exists for some time. There are other systems also, I will talk about it, which have this transient liquid phase nature. Okay. Again some pictures of this, again how this whole assembly takes place. You will have to prepare the silicon device on the back side with certain metallizations. Then you will have the foil, which is a silver tin alloy, and then you will have the substrate on which the attachment will take place, and you can form the alloys. So Again, in a very brief, the wire attachment process is the wire bonding process. In wire bonding process, there are different technologies that exist that allow you to do the wire bond. So, what is the aim here? The aim is I have a silicon die on which I have pads, and I have pads on my package substrate. So the dies, the pads on the silicon die are smaller, the die on the package is often slightly bigger, and I want to make an electrical connection from this pad on the silicon die to the pad on the package, right? I want a wire to come here, connect, come here, connect, right? So this is the goal. The goal is to connect on the pad on the die and connect on the pad on the wafer. So how can we connect? So to connect a metal to another metal, again, not all metals or any metal will work. There are specific combination of metals that work. If you want to connect a metal to a metal, you will have to provide certain energy, right? Metal and metal, if you just touch each other, they are not going to bond. You have to provide certain energy so that they can, depending upon different bonding phenomena, which we will again discuss shortly, they can bond with each other and form a continuous metal connection. So the bond process can be thermocompression. Thermocompression essentially means you are applying pressure to the metal, two metal pads, and heating. The heat and the pressure is enough to overcome any kind of resistance at the interface. Resistance in the sense that if there is any contamination or surface roughness which is not allowing the two materials to come into intimate contact, that is taken care by heat and physical pressure. You can also have ultrasonic, where you provide an ultrasonic energy to actually take care of the interface and allow the two materials to bond, or thermosonic. So these are the different ways. Thermosonic is essentially heat, pressure, and ultrasonic energy, right? So these are essentially different ways to provide energy to the system so that these two metals can fuse together and form a bond. Now, again, there are process of ball bonding, where you essentially first start by forming a ball that we will discuss later how it forms the ball, but you can see there on the top that the blue thing is the wire that is coming up, and then there is the head or the tip through which this wire is coming out. At the tip of the wire, you see there is a metal ball of the same wire which is existing. First it descends, and the ball makes connection with the pad on the substrate. The way again this bonding takes place between these two metal strips can be either of these processes, right? Then the tool goes up. Since the wire is attached, the wire extends, tool goes up, it moves into the other pad, and then it descends and makes another bond. So the first is the ball, the second is the wedge, okay? The first is a ball, the second is a wedge. The second we cannot form a ball, because the reason we cannot do it is the way the ball is formed is after this goes up, you have a tip which does not have a ball, and then it goes into a ball forming process based upon electrical discharge. So there is another tip which comes in, creates an electrical discharge between it, which heats and remelts the tip of the wire and forms a ball. And then it goes again and will do the second pad, third pad, fourth pad, and it can do it for multiple different pads. So this is the process of wire bonding, which allows you to connect these pads on the dies to pads on the wafer, right? And then comes the molding process, which is epoxy molding or plastic molding process. We will not skip this. Okay, so this was all okay for a very long time. This was probably one of the first technologies that came in for packaging and was okay for a very, very long time. But soon people realized that this is not a very good idea. As your devices started to become more complex, your chip sizes increased, the functionality on the chips started to increase. The reason is, when you do wire bonding on the devices, the wire bonding pads are essentially mostly limited to the periphery of the device, because what is happening, you have the chip, you put a wire, you come up, and you make another contact on the substrate. You cannot have second layer because then it becomes very, very hard because your wire now has to go over the first layer of wires and connect, right? So this is a limitation. Why this is a limitation? Because as your chip is becoming more complex, more functionality into it, you will have a larger number of IOs which are coming out of the chip, or larger number of ports or pins that are coming out of the chip. And that you cannot fit in the periphery itself. So then the idea of shifting to a area-based interconnect comes into place. When you can have interconnects or the pads which are coming out over all of the area of the chip, then it becomes much, you can have larger number of interconnects for a given area of chip, okay. So it increases your ability to have a larger number of IOs for a given chip area. Okay. Now the problem is you cannot do this wire bonding. So then we come to the idea of the flip chip bonding, where you will have an organic substrate. This organic substrate forms the layer where your chip is being flipped and connected. So these are the pads on the die. So this is your die and these are the pads. This can be now all over the area of the chip. They are not limited to the periphery only. They are flipped and connected onto this organic substrate. And this again is connected to your fiber substrate or epoxy glass substrate. Now, there is again a very interesting thing that you would see here, right, and I'll come back to this argument later also. As you see, we are going from each layer, right, our sizes of these interconnects are increasing, right, and this is also one of the traditional functions of a package, right. Our PCB, the pad or the line widths are much wider compared to the interconnects or the pads that are existing on the silicon device. Now, if I think about the traditional way of packaging the chips into epoxy molds and then connecting, a package functionality is to take that 10 micron or 20 micron pad connect on the chip, scale it to something which is more acceptable to the couple of hundreds of microns on the printed circuit board, and then take it back. And that is why you see here this type of scaling happens, where you have smaller connects, then it goes, as you are going outer and outer layer, it is becoming larger and larger. I will come back to this because the whole concept of chiplet is trying to resolve this problem of scaling of interconnects. The question that we'll talk about it, but what people are asking is, do we really need these multiple layers and scaling down? Because the packaging technology and the integration and the bonding technology is going to a level where we can handle bondings with accuracies of microns, right? So then this whole scaling thing is being questioned, because not only there is an issue that we are using a lot of scaling, which is probably not necessary, but there is also a problem that happens because of the materials that are being used. So if you look at this CTEs, CTE is coefficient of thermal expansion. If you look at these CTEs, you will see that there is a very large mismatch in the CTEs of the different materials. And why is that a problem? Because your chips are going to get hot, cold, hot, cold, hot, cold, and that is going to generate a lot of stress cycling, and that is not good for the interconnects and the system overall. All right, so again, how do we connect? Rather than this, we have to do wire bonding is connected from the chip to this using wires. Flip chip is you flip it and then you connect. There are tricks, there are challenges associated with this. One of the challenges that is associated is when you are doing the actual bond, you cannot see, right? Because it's a silicon and you have PCB underneath, you cannot see and align. So these tools become slightly more specialized and they have very specific techniques to get over this, okay? Okay. These features on the substrates, we call them bumps. There are different kinds of bumps and there are many different ways of forming them. We will skip this. How many of you have exposure to fabrication? Okay. So this was mostly for the students. So this is a standard fabrication technique in microfabrication technique where you use a physical mask, where a physical mask essentially means there are holes inside a substrate and you melt a material, right? So suppose I want to make indium bumps, right? I will melt the indium inside a very high vacuum environment. That will cause the molten indium to evaporate out and go and deposit wherever it can. Now, if I have a structure which is like this, a physical mask, then this molten indium will go and go deposited where I have kept it opening. So I can do this bumps by heating and melting indium and evaporating it and letting it deposit. So this is one way of doing this. The other way of doing it is electroplating. We can definitely do electroplating. So we make, again, open up, so we deposit some material, a template, we open up holes on top of the pads and then we plate. So then again, this allows us to make pads or bumps of different kinds. Another technique which is we like in research is a single on technique, which is based on laser melting. So you can buy this bumps, small bumps or solder balls, and this solder ball is a mechanism comes in and it allows one solder ball to come at a time. As soon as the solder ball is about to hit this pad, a laser comes in, melts it in air, and then a molten solder ball just gets deposited onto the pad. So this is a serial process, but it's good for it's good for us because it saves a lot of steps. It cuts down a lot of fabrication steps. But there are different techniques. Okay. All right. So okay. So again, this is the chip. There are metallic interconnects underneath, and I'm going to connect it to another substrate, right? And first is we thought about, let's have these solder balls which we are somehow forming on this and using this to interconnect to other substrates. So that is one approach to do it. The other approach to do it is to think about replacing the solder bump or most of the solder material with copper pillars, okay? Rather than having a big solder bump, so molten solder making the interconnect, we use a copper based pillar and a smaller amount of tin silver to actually make the connect. Why are we thinking about this? One of the reasons, there can be many, one of the reasons is as we are making this connection smaller and smaller, and as our requirement for the conductivity is increasing larger and larger, this material tends to become a problem. It doesn't match the material properties or the good properties of copper as well. It's not as good as copper, okay? So if we can have copper pillars connecting to each other, your electrical resistivities will have much better, you will have much smaller electrical resistivity in comparison to just purely solder bumps. So from there, the transition is happening where you are going into a pillar format, right? The other issue that happens is specifically in this kind of scenarios where you are doing with solder balls or solder bumps, you cannot make them smaller than a certain feature size. It becomes very difficult. You cannot bring them closer than a certain minimum distance, because this solder ball is going to completely melt during the attachment process, and you have to give a certain allowance for that these solder balls will squeeze and increase in size. So placing them, making them smaller and placing them closer to each other increases the chances of interconnects, right? So there are challenges in those formats as well. Whereas if you are in this format, this does not liquefy the whole pillar. So your resolution accuracy can be maintained much better in this. So you can have much smaller pillars, much closer pillars with each other. So this is how it is done. This tin silver alloy on the copper pillar is primarily there to make the bonding easy, because the tin silver alloy melts easily and bonds easily. That's one purpose. It also serves another purpose. Any guess? So if you are thinking about pure pillar bonding, right? So if I only had copper pillars on one side, so basically I have posts of copper on one side and I have pads on the other side. I try to bring them together and bond them. What is the challenge? Matching of? What matching? Matching what? Position is flip chip bonder will take care. Surface contact. CT is a whole system problem. The problem that happens is if you don't have a melting system, in this case something is going to a liquid phase. If you don't have some material which goes through the liquid phase and you have a solid-solid bonding, that essentially means that your height uniformity has to be very good. Okay? Because if your copper pillars are not of the same height, then you don't have that allowance, because you have no melting phase, right? So if in this case, if a copper pillar is slightly smaller somewhere else, then what is going to happen is this tin silver is going to get squeezed a little bit more and allow that part to bond easily. Now if you have copper pillars everywhere and you are doing a solid-solid bonding, you essentially need to have a very good allowance for your thickness accuracy. So the thickness variation can cause problems. Okay? You will lose connection integrity. You will not bond everywhere equally. So these are some of the challenges when people are moving towards pure metal-metal bond. All right. So this is a solid-state diffusion bonding. Metal-metal bonding is a solid-state diffusion bonding. When two metal comes into contact with each other, gold does it very well. Copper also does it. Okay? So you bring two gold surfaces, you heat and apply pressure. The interdiffusion of gold within itself is very high. So very soon this whole interface will be gone and you will have a single metal layer. So this is the idea behind where people are trying to look into direct metal to metal bond without any without any solder layer. It comes with a lot of good properties. One is definitely you are losing out these intermetallics or the solder alloys from between. Second, so it gives you a very, very good electrical property across this interconnect. The mechanical strength is also better compared to alloyed materials or intermetallics. Underfill I'll skip. All right. Now, okay, underfill I cannot skip. So now let's think about that scheme. What we have the substrate, we have the chip. The substrate and the chip come into contact, nitrogen is flowed, and you do the bonding, and the bonding takes place. Now, very often, only if you are bonding only at the electrical pads, the strength is not good enough to hold the chip into place against mechanical vibrations or shocks. So what is done is another liquid is flown inside, which is called the underfill compound. This underfill compound will go in and epoxy, and it is an epoxy, it will mechanically hold the chip and the top together. Okay. Now, so there are, again we will not discuss, but there are certain issues with them. To address those issues and the issue of having that underfill compound, and to think about again a next level. Right now what we are doing is we are still doing this one chip on top of each other, where you can clearly see there is a chip which is sitting on another substrate and they are bonded to each other. A question can be asked, can we somehow take the integration scheme to a level where there is a seamless transfer of active layers from one device to another, right? And all of these can be possible with what is called the hybrid bonding. So this is again, as was mentioned in the last talk, the hybrid bonding is a very active area of development, and the idea is, if you look at the top of a silicon device, right, you will have areas where there are pads, so this is copper, and you will have areas where there is passivation, right, and in this case it is some oxide or oxynitride kind of material. Now if I can come up with a scheme, so in the previous scheme we were only connecting the metal to metal, right, we were connecting the metal on the top chip to the metal on the bottom substrate. Now people started asking the question that if I can form a bond between the metals and the dielectrics, then I can have a system where it becomes very uniform in terms of material. So it will look as if they have been deposited on top of each other, or they have been made like that. So, but there are certain challenges in doing this. One of the big challenges is oxide and copper have very different coefficients of thermal expansion, right. So how do you exactly do this bond so that you bond the oxide and the copper at the same time? So then everything gets bonded from one chip to the substrate. The passivation layer also gets bonded, the metal also gets bonded. So in this case, what is done is actually by some CMP process, you take away the copper and you reduce the height of the copper by a very small amount, okay, a very, very small amount. This is in nanometers. So the height difference is in nanometers. Then you go through an initial bond. In this initial bond, the passivation layers actually bond with each other. So oxide or oxynitride layers, they bond with each other. And subsequently you go through an anneal step. In the anneal step, the copper expands and connects with each other, and you can get the metallic connection also. So this is what is called hybrid bonding, and the beauty of it is everything gets bonded very uniformly. Okay, I'll show you some slides from IMEC, and this is an hybrid bonding where the metal is bonded and the dielectrics are bonded. People who have looked at cross sections for devices before, you won't be able to tell whether they were as fabricated or they have been bonded, okay, because this now becomes uniform materials. There are a lot of benefits. Again, you can have, you don't need that underfill material. You can form connections at much smaller pitches. Your thermal properties become very good because now you have this continuous dielectrics also. Your heat transfer vertically becomes much better than traditional stacking with pillar based bonding and filling it with underfill. So there are a lot of different benefits. And again, as I was mentioning in the early part of the lecture, that today bonding accuracies are so good, right? Here you can look at, this is a 2-micron scale. So this alignment is sub-micron scale alignment people are doing. So you have a chip, another chip, you don't see, but you can still align it to an accuracies of less than a micron. So yeah. So so in this case, this so these steps, in my personal opinion, these steps are easy. This is the hardest step, where you precisely have the copper a few nanometers below your dielectric layer. Materials is a big challenge also. I will not undermine the material problem. These layers have to be a very specific kind of oxynitride so that they get bonded in that environment. And the challenge here is this gap, because initial bonding you will only bond the dielectrics. Only in the anneal time this expands and makes connection with each other. And the reason why you want to do this is you cannot have that whole flat, because then what will happen is during the initial bond, this is also high temperature. Okay, this is also high temperature. This is not as high as this, but this is also high temperature bonding. When you're doing this step, if the copper starts expanding, it will start pushing your dielectric away. So you will have cracks or beaking kind of effects if your copper polishing is not done right. If you polish too much or if you reduce the height too much, then this joining will not happen. So this is yes, metal. No, these are not shadow masks, these are standard lithography techniques. So shadow mask is only stops when you are doing large features or the large balls. So those were the initial processes, right? Even there, if you want to do smaller bumps, you cannot do it with shadow mask. So copper pillar bonding is happening today. No liquid phase, pure solid bonding. Copper gold. We also do. Copper we are not doing, but these are very standard. Pillar bonding processes are very standard today. So inkjet printing is not there. There was a company called Microfab which tried it. So what it used to do is it used to use a heated inkjet head, okay, and tried to like inkjet the solder ball. But that technology has not gone far. One of the technologies which has commercialized was the one where you have these pre-made solder balls and you melt them in air using using laser, and then you deposit onto them. This company is called Pactec. You can look it up. So they have equipment which can do it. So what's the time? All right. Okay. Thinking if I should. Okay, I'll cover this part also. So all right. We had gone a little ahead. We'll step back a little back and talk about fan out wafer level packaging. Okay. Again, this tries to address the concept of the size discrepancy, right? Our PCBs have larger feature sizes and our chips have much smaller feature sizes, right? Now the problem happens is if I try to integrate a chip directly with the PCB, the pad sizes will not match and the feature sizes will not match. And there what is required to be done is we need to make the interconnects from smaller pad sizes to larger ball sizes which are spread by a certain distance, right? Large distance compared to here. So the pad to pad spacing here is small, ball to ball spacing here is large. So what we are doing is we are scaling the interconnects and the pads from a smaller dimension to a larger dimension. And one way to do it today is called a fan out wafer level package, and what it happens is you will have a chip, you will have the epoxy mold, and then on top of these there are certain layers which are existing with the balls on it. In contrast to the conventional packaging that we were discussing before, in this scheme there is no packaging substrate. Okay, so what we were doing, we had a packaging substrate with leads or no leads. Chip comes and attaches on that packaging substrate and then we fill it. Here there is no packaging substrate. The epoxy and the chip themselves function as the packaging substrate. Okay. You can buy these chips today. If you look at Mauser or DigiKey and if you search for WLCSP package, these are the packages. They tend to offer you the smallest sizes that is commercially available today. The way it is done is you first have the full wafer which has been fabricated, then you dice it, okay. Then you take a temporary, there are 3 different approaches in bigger picture. You start with a temporary substrate, you apply some adhesive or a tape which is adhesive, temporary adhesive. Then you put the chips face down. You can do a level of testing before it, so that in this step you only take the known good dies. The chips are faced down and separated. In a wafer in which were fabricated, they were placed close to each other. So now you take them and reconstitute them on another wafer at a certain distance. Then what you do is you pour the mold and form the mold on top of it. Now what you can do is, now you can remove this carrier. This molding compound will form a wafer of its own with the dies embedded into it. These are called reconstituted wafers, right. Now what you can do is, now you can start making the interconnects on them using the standard lithography process and electroplating process. So you flip it up, flip it backside, like you flip this, the dies come on top, you put a layer of dielectric, etch it, electroplate metal on it, make your interconnects, then again keep repeating the step to form the interconnects. So again, there are 3 different techniques. So you can have face down die first, face up die first, and you can have face down die last. So there are multiple different approaches to finally achieve at the same thing. So here what is happening is, you have the die encapsulated in the mold, which is the epoxy, and then on top of it your interconnects are fabricated, which allow you to redistribute the connection to a larger pitch size or a larger feature size. We will not go into this, that was only the concept. When you actually dive down into the process, this becomes significantly much more complicated, and lot many steps come in and lot many challenges come in, which need to be addressed, and there are many different approaches that people have addressed. Again, using these approaches, as I was saying, 2.5D integration today is a reality. Lot of devices that are being used today have these kind of integration, where you have chip 1, chip 2, they are getting interconnected by another substrate which is here, which is called the silicon interposer. There are different terms, but interposer is one of the mostly used term. This silicon interposer, what it does, it again does the wiring, like you do in PCB. This is the same wiring, but is getting done on a silicon substrate using lithography techniques. Benefit, compared to PCB manufacturing technique, lithography allows you to go to much smaller features. So you can have wiring which is in the order of width of 10 microns very easily. That's not a problem. So you can place these chips directly next to each other, interconnect them with very low pitch bonding. So as you can see, the small dots, each of these small dots is a pillar which is bonded to another pillar on the other substrate. Then you have these larger pads which are getting connected to the package substrate, and this package substrate then finally has the solder balls. This solder balls will go onto your PCB. So this is the multiple layer of packaging that is happening, and this is generally being termed as 2.5D integration. All right. Now I'll just touch this idea and stop here. So the idea of chiplets is essentially what the question that is being asked is the way we overall integrate systems, how we build systems, right? We are having this packaged chips and then we are integrating them on PCBs. Now what is being asked is, and the interconnects have to be scaled. As we said, dies, connects on the dies are smaller, on the PCBs are larger, so your pads or interconnect size, metal size is from 10 microns going to 200 microns and then going back to 10 microns. Is that all necessary? So what people are envisaging is can we directly take these devices, dies, silicon dies, right, and then integrate them on a substrate which is made out of silicon rather than silicon or glass. Glass substrates are also there. So, silicon or glass substrates, but the interconnect in comparison to PCB, which does not have that kind of resolution, you make it on silicon, you can have resolutions which are very, very smaller, right, much smaller today. So, and then you bond these individual dies together to form your system. So, your system now becomes a set of silicon devices which are attached on another silicon substrate. Now, for mechanical protection, you can finally put everything inside some other kind of package, but your overall system becomes very, very small, right. So, this is the idea of chiplet and chiplet integration. I think the thought process is that in some time in future, there will be very standard dies and standard protocols which will come in, and that will allow anyone to develop very high performance systems just by ordering these chiplets and assembling them in a manner that you want to assemble. Okay. All right. So, this is again, these are some pictures from UCLA work that has happened there, where they are trying to connect this, and one of the goals is one of the crazy goals is, can you make like a whole workstation on a silicon wafer? So, you have different kinds of chiplets and you just assemble the chiplets on a wafer and come up with a computer. All right. So, with this I will stop and take questions.
If you want to have some optical elements also in there, will it be an extension of this process or will it be a completely
So, this is ongoing. I'm not working on it, but there are, I don't know how exactly the optical interconnects are getting interconnected with the electronics. It's a fairly complicated process because you are going to change the energy domain, right. You are coming from light going to, so you have to have detectors, you have to have generators, you have to have modulators, anything, and what part will stay in optical domain like a photonics domain and what part will stay in the electrical domain is, again, I don't know, but this is active AES, as the last talk also discussed. So, this is something I found online. I don't have much idea about this, but this is something that Intel has put out, where they are trying to look into photonic integrated circuit with their substrate inside the package. So, this is definitely happening, but I don't have much idea about that. Like the internals of the technology I cannot talk about.
So even I won't have much of an idea, but I can add a few comments. Safal has a startup, Lightspeed AI, who worked on it, and the basic proposition is that using light and photonics, they are able to pack a far higher bandwidth performance from the photonics chip that they are making as compared to the conventional electronic chips. The way it is being done is they have transducers which convert the electronic signal to photon. There are laser guides which are light guides which are being used along with lasers to actually make that coupling happen.
Okay. Yeah. So, thank you everyone.
A few other points I can share on the advanced packaging. So one of the key drivers on advanced packaging as well as the entire packaging ecosystem is the cost per interconnect. Money makes the mayor go, and that holds true for the ATMP sector also. So all the end users, they keep a lot of pressure on the ATMP OSAT vendors to cut down the cost per interconnect, which is why as you see the evolution of the chips, some of the functions beyond some of the changes beyond the functionalities are aimed at cutting out the cost from the system, from the package. So you've seen how as you get into the fan-out packaging mode, you are cutting out the interposers, you're cutting out some of the other costs. How over the years, the gold wire has gone from the wire bonding. No longer you look at wire bonded system using gold wire. You don't use some of the earlier interposers, and you don't use some of the underfails anymore in the advanced packaging domain, because you are cutting out all those costs as you're going in for more and more advanced packaging. You are also going for actually systems where you are integrating at a very high productivity rate. So literally, instead of doing a dicing and then placing each die and then trying to uh, uh, complete the process of making the package, you are taking the entire dice, reconstituting on a fresh substrate, one stroke coating, taking out the redistribution layers, RDLs, out on your structure, and then you are going for this advanced packaging. The interesting thing that I do want to share is a lot of work on advanced packaging on that is being done by Applied Materials in India. So our panel level packaging tools or applied materials panel level packaging tools are actually a key enabler of the new paradigms in that area. They are mind blowing. You can just imagine if you are reconstituting on a wafer. Prasanjit ji talked about going into wafer scale packaging or chip scale, wafer level packaging. But that's happening because you reconstitute the dies on a 300 wafer. And you reconstitute it on a 300 wafer because what you were doing is you're using the 300 front end process to do the recoating, to do the CMP, to do all those front end type processing on making that package. Then they have moved from there to a rectangular substrate, a glass substrate, on which they are going to reconstitute it. So imagine going from a 300 wafer, you're going to 300 by 300 rectangle. Just in that process, you are changing your, increasing the number of dies you're going to process at one stroke. Then you're going from there to 600 by 300. And then you're going from there to 600 by 600. Okay, so in that process, you have improved your scale of production by a factor of almost 8. Just imagine that. You're changing your scale of production by a factor of 8. Your costs of production are coming down that much more. So that is the new paradigm that is actually evolving. It is predicted that advanced packaging in about 4 or 5 years time, by end of 25, it is supposed to be it's almost the same size as the conventional packaging. But maybe by end of next year, it'll be a little more. Both sides are growing, but the growth of advanced packaging is marginally higher. And it will have a different positioning strategically in about 5 years time. So that's about it. The right thing after this is, let's go for tea. I'm sorry. The right thing after that is thanking Prasanjit ji, Dr. Prasanjit. Thanks. I learned quite a few things there, sir. Thanks. Yeah, a major
announcement. I just want to know, like, how many are the faculty members here, and how many are the students from outside Bangalore? Okay. So outside Bangalore. So basically, like, this is to check, and explore the possibility of the visit to the CeNSE lab tomorrow morning, 9 o'clock. So maybe like we will have 2 batches. So during the tea, probably you can go and register yourself at the registration desk, right? And we will see like how many can be accommodated in the first lot, second lot, 3 lot, like that. And then the people who are like from local Bangalore, so for them they can also register their name, but then we will arrange for their visit to the labs only in the next week. So but that will be done. So we don't want like the Bangalore people to be left out, but yes, they will be like very much part of that. So all those who have come outside Bangalore, they should go tomorrow and see the lab first. Thank you.
Sandeep, you can ask the rest of the people to come in. I'm starting with immediate effect so that we finish well on time. Uh, this afternoon session, I'll be taking you. So, uh, Dr. Prasanji did a great job of introducing advanced packaging and packaging fundamentals, the various types of you know, device packaging technologies that are there, the thought processes, the issues in developing the packages. But I'm going to take it away a little differently. I'm going to take reference to the actual manufacturing processes that take place in the current you know, projects that are cleared by the India Semiconductor Mission, and from there I'll take one specific manufacturing process unit and I'll deep dive into what it means from the manufacturing point to do that particular process. So, without further ado, let me start. Let me again tell you, the whole purpose of that video was twofold. First, to get you all to come back into my world, and the second is actually to take you through this key message. We are trying to give you something new. Whenever you encounter something new, there are a lot of people who will say no, you should go back to design, you should only do this. You know, there are always lots of doubts you will have, you know, self-doubts on those new projects that you are going to do. But define it in your mind what your long-term vision is. Then start navigating towards it. Some of these are only steps towards that final goal. Okay, and let me tell you, there are some people who succeed, you know, who have this saying that we'll only succeed if we do engineering, we'll do this, we'll do that. There's nothing like that. Okay, there are people who do X, people who do Y, path in the life. Only time tells you who is the successful one. Okay, so let your destiny flow from your interest. Let a plan be there in your mind. The destiny itself will be guided separately. I want to take over the next 30-40 minutes a quick message on wafer dicing. And wafer dicing is something which has been touched on a few times during the day. It's a key part of the conventional packaging process. It's a mechanical process. Okay, it's slowly getting you know, replicated or adapted with the versions of it which are a lot less as mechanical as they were in the conventional packaging. What you see on this slide, that side are some of the components which will be there in a typical conventional packaging process. These are still steel carriers, okay, on which you mount this tape, and on this tape you place the die, the wafer. Okay, and then you are taking it through the dicing process, where, as Prithvi talked of, you will have water which will be flowing on the wafer to cool it, on the saw to cool it, okay, and on the post saw process to remove the debris, the you know, the silicon debris which would get created, because you don't want it to destroy the dies which are there on the wafer. And this is the machine, typically one of the machines which can actually be doing the dyeing. It is pretty much automated. It's not like you're actually doing a mechanical sawing. In fact, the saw itself doesn't move, the diamond saw itself doesn't move. It's the chuck, the table, which moves. Okay, and the entire thing is pre-programmed in this machine. Robotic arms will make this entire execution happen, and there is a lot of data that is available which an engineer has to take into account when he is setting that particular machine for a particular run. We'll discuss those things in the next 20 minutes or so. So this is a typical manufacturing process flow. You heard versions of it during the day. There, when the factory, at the starting point of the process in the factory, the wafers come. Okay, so when CDIL is actually making those silicon carbide you know, packages, he said we are importing those silicon carbide wafers into our factory. Okay, those wafers have to be inspected before they get into the manufacturing process. You can't rely on your foreign vendor having sent you the right wafers. You have to do the material characterization testing that this is meeting the requirement of my process. Once they are qualified, a lot of times you might be doing something called back grinding. You know, the thickness of a wafer can be almost, it's a little less than a millimeter, okay, about maybe 750 nanometer or so. Now this wafer will have to be ground. They will thin it for a lot of applications. There will be back grinding done, so die remains intact, but they will back grind it, polish it, so that it can actually be used in thinner packages. Okay, it is prepared for other applications. Then after that, you do the wafer dicing, which is the process that I am going to take a deep dive in. After that, you go for die attach, do the wire bonding on that die. You saw some of the visuals in Professor Prasenjit's slides. Again do metrology, then take it into molding. Then after molding and buffing, you get into the marking and the subsequent processes. They do laser marking, package singulation, pick and place, testing again, tape and reel, and ship. This is the process that typically will unveil out in CeNSE factory, in Tata's factory, CG Power factory, CeRSA, you heard CDIL. This is the core process which will run out. So in the group that is working on this at the center, I'm leading that group for the manufacturing skills for semiconductor packaging, and we have clustered these into different job roles. Now I'm not sure if you can see it at the back, but what I'm saying is the first 3-4 processes we say that is die preparation, then die attach, bonding, and laser marking, testing, and finishing. Now when you are doing a job preparation, when somebody is getting trained on a particular unit process, in reality you do not want at the factory level, the company will not want a person to be trained on just one thing. Okay, so if he is trained on one thing, he is a technician for that. Okay, but if he does all the related trainings in that particular domain, then he becomes a little more a specialist. Once he has done everything relating to this, he is an expert, because in that process over a year or year and a half that he has gone through all this, he's actually picked up experience, he understands the process, and then he is an expert. And then over a period of time, he just revalidates, says I have done so much of experience, I have done so much additional knowledge picking in this domain, and he is groomed further and further into the execution. So today I am taking you deeper into the wafer dicing engineering process. So as I said, the first step that takes place in after you have got your wafer in, and I am assuming that it is done, that the grinding is over, I am talking of wafer dicing. First thing is mount it on a steel carrier. Now this can be a steel carrier, it can be a plastic carrier. You mount it using a mounting tape, okay, and on that mounting tape you will mount the wafer, and then you have a scraper, this sort of a scraper. Literally what you are doing is scraping the mounting, the tape, so that any bubble that is there, that is eliminated. That is the simplest way to look at it. In some of the semi-automatic machines, on the automatic machines, they may have a roller which may roll and try and eliminate that bubble, but this is the mounted wafer you will get at the end of it. Okay, some terminologies. This is a wafer. Some of you would have seen it. Tomorrow you will go into the lab. Some of you will get to actually see this thing physically also, but it's available on Google. Nothing to it. Available in number of sizes. Typical sizes are 6 inch, 8 inch, 12 inch. Okay, But you have smaller coupon size also available. We call that coupon size, 4-inch, 3-inch, some 2-inch are also there. But the point is, the standard ones are typically 150 mm, 200 mm, and 300 mm. Okay, and inches is not the right terminology for it. Okay, it's not exactly 12-inch. 300 mm is not exactly 12-inch. It is 300 mm is the right word. Okay, this is a very thin slice of either a CMOS silicon or compound semiconductor, gallium nitride, gallium arsenide, or silicon carbide. Or if you're doing LED dicing, then it is LED sapphire, substrate. The die size is a key parameter. Okay, that is what your die footprint is on that wafer. Wafer dicing is the process of sawing and slicing it into individual dies. If you take a 300 mm wafer, if you have 1 millimeter by 1 millimeter die, how many dies will be there on that wafer? Can somebody guess and say? On one 300 mm wafer, how many dies will be there of size 1 mm cross 1 mm? Assuming a separation between dies of maybe 50 micrometer, 50 microns. It can be how many? 2700. You are giving a number which is not, it's moving towards the right number. The right number is 50. The right number is 55,000 dies on a single wafer. Okay, so you're getting to see the challenge out there. Single wafer can actually give you so many devices. Okay, so fab, when it says it's going to do 50,000 wafers a month, each of them capable of servicing so many devices, the sort of market you are addressing is mind blowing. Okay, saw street or scribe, this is the area between the individual dies. There will be one die on it, number 3, which is actually going to be a test die. Okay, grit is the is a specification for the diamond particles on the size. Concentration is a specification which says how many diamond particles in a given volume. Edge roughness is actually the condition of the top, bottom walls of silicon after you have done the sawing on it. Okay, edge loss comes because if you take this dies, you will find that you are not able to use some part of it. The die cannot come on it because die is rectangular, this is a round area, so there will be losses. So if you take a look at edge die, you know that these dies are all bad. This is an edge loss. Okay, and flat zone, there is always a flat zone. So the flat zone is an area which is marked to define the orientation of your wafer. So you can have a flat zone. In 300 mm, you will have a notch. That notch will tell you that this is the place from where you start orienting the wafer. Okay, so now you have got a feel of the dicing definitions. Let's actually get on to the equipment. We covered the rings. These can be steel rings, or they can be made of plastic material, PPS, PA, polyestate, PBT, which is poly something. The notes will be shared back, but you have which are two types. You have a mounting tape, which is the blue mounting tape here. You will see this in a lot of actual production areas. If you remember CDIL presentation, their mounting tape was blue. Their video showed a blue mounting tape. Okay, if you go to the CeNSE lab and see the mounting that they do, they are using the gray, silver gray mounting tape. This is the normal mounting tape. The silver gray is UV ultraviolet mounting tape. It will actually change its properties when exposed to light. Okay, that is the significance of the UV tape. Then you have a carrier on which you can mount and move these wafers. You have seen this in CDIL setup. They were showing a semi-automatic mounter. When you go to the CeNSE tomorrow, you will see this device, the semi-automatic mounter. You will also see the automatic wafer mounter. Okay, and basically it is very simple. It's nothing. It's a place where you put the ring in, you put the wafer in it, and you have that roller. It mounts it properly. Just that's what it does. Okay, and well, that's the semi-automatic one. This will have a little higher productivity. Not everybody needs the automatic one. Why do you think a CDIL is only having the semi-automatic one? Because at the end of it, I don't think they are having that sort of a wafer load requirement. To give you an idea, the world's largest smart ID card factory is in India now. It is in Noida. Okay, they package 66 crore smart cards a year. 66 smart cards a year. Every credit card you have in your pockets, every smart card that you see would be having would be packaged in India by that particular company. Okay, I'm a consultant to OECD. I got the OECD teams in India in September, and I took them to that factory, and they were looking at it. Oh, my health card in France is actually coming from here. Oh, this particular card is getting packaged here. The army smart cards are getting packaged here. I tell you, India actually is doing amazing things. The fact of the case is that particular factory, which is doing 66 crore smart cards a year, which translates into 5.5 crore smart cards a month, will require only 1000 wafer starts a month. Okay, 1000 wafer starts a month, which basically means to how much? 30-40 wafers a day. Okay, 30-40 wafers a day. 30-40 wafers a day, you don't need a big automatic machine, and that's why they're not having it. And that's someone who's doing 66 crore smart cards a year. So the key message, nothing wrong in these things. Whatever meets the requirement is what is required. You don't have to spend money just for the heck of it. And the wafer mounting process, a lot get deep into it. Simple. There is a vacuum. The carrier is mounted on it, pulls the tape, and that yellow thing is actually the cylinder which rolls over and makes sure that a tape is pressed on that wafer, and the wafer sticks on it. The defects that come are shared here: air bubbles, cracked wafer, any scratches, visually inspected and weeded out. The wafer dicing process is simple. You want to actually slice the dice on the wafer, and it is placed on a tape. Okay, tape has a thickness. Your dicing is done in such a way that you dice into the tape, but not through the tape. Okay, so that is again one of the engineering measures that are there on it. You have methods of dicing. I'll touch base very shortly on it. Sawing, the saw doesn't move. It is the chuck, the table on which the wafer is kept, that is moving in the sawing process. And then there is a washing of the wafer that takes place. Defects that come in, you have a sawdust contamination. You have ultimately, the wafer is what? It has got ultimately a metal layer on it also. Okay, the metals could get peeled, electrochemical corrosion can take place. There can be chipping. This defect is called chipping, irregularity. It can enter into the active die area. It crosses the saw street. If it enters the active die area, then it is a defect. This one is accepted. Okay, it need not be accepted in some of the other versions of it. This is rejected. It's entered, the chipping has happened here, rejected. Backside, front side is easy to control. Backside is a little more difficult. It might be that your backside breaks like this. This is rejected. Sidewall chipping again can impact the active die. So these are some of the defects in wafer sawing, and the entire objective of the technician is to make sure that he balances between getting a good yield and getting more dies cut. See, you can increase the speed of dicing, but if you increase the speed of dicing, your defects will happen. So you have to balance between the dicing speed and the dicing quality that you get. Okay, and to do that, there are issues on how you are going to dice. Will you dice at one stroke? Will you dice it in 2 times? First I will dice like this, then I will dice deeper. Okay, those are multi-pass step cut dicing, and I will again talk of it a little later. But you actually have all these things, and they are dependent on the substrate that you are using. Certain type of substrates you have to do step cut. Okay, certain type of substrates you can manage with a single cut. So these are again nuances that the technicians have to understand. Your final quality of output is subject to the type of wafer you are looking, the sort of interconnects you have, what sort of photochemistry is used, what sort of blade is used. This was covered by our friend Prithvi also, the grit size, the grit material concentration. The process parameters we did not cover. You have to actually be aware of the different dicing modes: single cut, double cut, dual pass, step cut. Blade speed and chuck table speed are relevant. There is a relation, and you actually will get manufacturers' graphs for it, and you will have to customize it for your specific process, specific material that you are going to work for, and you will have to define your cutting depth. Input materials will be your mounting tape types. The DI water quality makes a difference. The rate of flow of water makes a difference. Anti-corrosion, anti-pitting additives that you put in that water make a difference. So all these are stuff which make help in building that final output quality. Wafer mounting, you have to take into account your lamination void free, wafer to tape adhesion, mounting tape materials that you are using, the sort of die attach materials that you are going to use. All those are relevant inputs for this. And the saw machine itself, what sort of saw machine you have? Are you having stable or vibrations? Is it rigid enough, or it will have an impact on your final dicing? The cooling system design, the blade mounting and balancing, is it a single spindle sawing device? Is it a multi-spindle sawing device? All these things are relevant. So you have to balance between yield and speed. That's the key message on this. Okay, this is a typical graph that could be there. You have 2 different types of blade. It shows that this particular the blue one, SD3000, gives you the lowest, what is it? It gives you the lowest top chipping, at 45,000, RPM speed, while the SD2000 blade is giving very good results on backside chipping with 30,000 speed. Okay, so you have those tables, those data points are available. If they are not available, you will have to test and define those data points, and then you go ahead and select the process parameters to run your dicing process. Okay, the role of DI water, cool the blade, cool the dicing blade, cool the substrate, cool the remove the silicon debris. These are some of the key elements. Prithvi has already covered the significance of DI water in the process. Mechanical versus laser dicing, very simple. Mechanical dicing it's actually a diamond saw which is actually physically cutting it. Here it's a laser beam which is cutting it. In laser dicing, there is another process, the stealth dicing. In laser dicing, still you have your cutting on the top, but stealth dicing is interesting, especially when you go to lower, thinner wafer types. It will not just cut on the top. It will operate in such a way that it will cut below that top layer. It will actually cut below the top layer. And because it is going to cut below the top layer, you again have certain process advantages, better yield. So depending on the application, you may actually end up using a different dicing machine. But take a look at the cost. This might be a $250,000 to a dicing machine application. This is $1 million dicing machine. Okay, so again, all these things are different. So this is just to share with you some of the dicing technologies that are there. I covered stealth. You've got a feel of laser dicing, mechanical dicing. There are plasma dicing, ultrasonic dicing, water jet dicing, and let me tell you, there are combinations of these also. Okay, there are combinations of these dicing mechanisms also available as equipment in the marketplace, used in specific conditions. I've already covered this, dicing quality versus dicing speed, the significance. The process control and rigorous metrology are really the key, because as I said, ultimately market says give me the lowest costing output, says give me the lowest costing output. If you do not meet the yield that is required and the productivity that is required, the profitability of the project goes for a toss. So these are very key parameters, and the technician plays a big role in helping decide that. So I think I covered first batch of input on it. Let me see if I can give you some more insights on this. I'm going to show you a brief video.
There are 4 dicing methods in wafer sawing process. So the dicing method will refer to the machine capability. So current in the market there are 2 machine available, such as the first one is single spindle dicing machine. This is single spindles mean one blade. Means same like the disco machine that we have in our lab, the AD3340, which is one blade, which is called as single spindle. And the second one is double spindle dicing machine, means there are 2 blades in a machine. Alright, so there are 4 types of cuts.
Can I just
for wafer sawing? One is single cut, number 2 is dual cut, number 3 is dual pass, and number 4 is step cut. So I will explain later what is all is about. So in terms of the capability, single spindle dicing machine is only capable to do single cut and dual pass. For dual cut and step cut, you do not have the capability to do so. For double spindle dicing machine, it can do all cuts. Alright. So what is single cut actually? So single cuts mean, so whenever if you have like 50 lines to cut, the machine will cut one by one. Okay, one cut, then the second cut, then until 50 lines it will finish. Alright. So how about dual cuts? The dual cuts, the machine have 2 blades in a row. So one time 2 blades will come out. So mean if you have 50 lines, you will cut to 25 lines, then it will complete. So mean it is faster, 2 times faster, right? Okay, one time cut 2, then it will be faster, rather than cut by one by one like single one. So dual cut is much more faster because one time it cut 2 times. Alright, so we come to dual pass. What is dual pass? Dual pass is using one blade, then it will cut the same position 2 times. Alright, the blade thickness is same, one then one more time. Cut 1 into how many percent into wafers, and cut everything into the mounting tape. Alright, so this is dual pass. So step cut. Step cut is using a thicker blade on the Z1 and a thinner blade on the Z2. See? So thicker blade, then thinner blade. Thicker blade, then thinner blade. This is called step cut. Alright? So why we need to do step cut? In terms of compared to the single cut everything, alright? Okay, for example, if you want to cut a very thick wafers like 600 micron wafer thickness, yeah. So for example, so for top side chipping, we can see when you single cut there is no issue, so it is accept, and the step cut also there is no issue, so it is accept. However, for backside chipping, it is a failure for single cut. And you can see the step cut is very smooth in terms of chipping compared to the single cut. Why? So you can imagine this when you want to do a karate on the chopping board, a thick chopping board. All right. For example, the chopping board is thick. Then if you want to chop the board into two, you need to have a high pressure on it, and the result is not so good at the back because it is so you need to bang it so hard so that it can break into two. So step cuts means you cut the chopping board 50% first. You cut into 50%, then you do a karate. It is much more lower pressure to break it into two, and the result is also much more better. So the pressure to cut into the thick wafer causing the chipping become higher. Alright, so this is like the diamond blades, and this is the stress zone. So this is where the cracks initiates. Yeah, so take note, the diamonds and the blades actually the diamond will accumulate the mounting tape component as well, so that it will produce more stress zone into the exterior, causing it is more chipping area. Alright, okay, so let's go to the back side. This is when you take out one die from the wafer and you inspect. So from the high backside chipping, you can see the backside chipping is failing because the spec is less than 200 micron. So this is, you see the chipping is more than, it's about 250 micron, is considered fail. Alright, for step cut, it's more smooth, very nice. For sidewall chipping, it's still acceptable because it is the reject criteria is 30% of the wafer thickness is about 180 micron, and the chipping is only 94, so it can accept. However, for step cut, you see a very solid sidewall performance, yeah, compared to the single cut. Then this is why cut method is very important to have a very good quality in terms of soil performance. You want to define to use which method.
Okay, this is, I'll just cover what it is saying. You have a height of the build, you have the chuck table, you have the mounting tape, you control the point to which the your dicing saw will go. You also control the limit to which it will cut in the mounting tape, which is actually going to be between the wafer and the chuck. So you define those heights, and that's how you cut. We will not get into it right now. I do want you to take a feel of the way the qualification packs are coming up. If there are any questions, I can take it up, but I can share with you how the qualification packs are coming up now. Any questions at this stage? So if there are no questions, I have nothing major additional to share except some of the work that we are doing on this. and let us see wafer dicing. So when we decided to develop the course, we had the basic elements, and then we started fleshing it out further. We have manufacturing process flow for semiconductor packaging, equipment overview, materials and blade, wafer mounting. My fellow colleagues in the team which is working it, they have added some comments, which is okay. Dicing process, process parameters, dicing techniques, the quality control, safety protocols, quality control inspection, troubleshooting and maintenance, sustainability and environmental, and where all the hands-on can take place. Once we have this, I think we have something which can be used by the universities, by the next generation to go ahead with a lot more practical experience. Just want to share with you, sometimes there's a lot of this thing that our institute needs to have that lab. Okay, it's a huge investment. It's a huge investment. Okay, to my mind, it's not required. If you have this, if you have the videos, if you understand the engineering part of it, you just need some exposure to the entire equipment. That need not be an exposure that runs into months of handling. Fact is, even in institutes which have it, it's not that the students are going to get months of exposure on it. In our case at Manav Rachana, what we are doing is we are affiliating with industry and institutes who are having the equipment. Okay, so I talked of this company in who's the biggest smart card manufacturer. We'll have an affiliation with them. We'll actually send our students to them for internship and dojo practice. Okay, if they are there for a week, once they go with all this knowledge, on the site they can pick up whatever is required very fast. There is no rocket science to it. After all, it is a semi-automatic mounting machine that they have. The disco machines are all very automatic. They need to just understand how the wafer has to be placed, how it has to be programmed, and that's all. If they ever go back into that industry, then there will be very specific tools that they will be working with. They can pick up that knowledge very fast. If they understand the way the entire engineering is there, the parameters that have been verified, that's all that is required. When industry says that, I get people who are raw, of course, if they don't know this, if they are only taught basic device physics, energy band diagrams, okay, then they will be at a loss when they go into the industry. But if they go with this knowledge, then they can be running on the ground far faster. And that is what we are trying to say. That's what we are trying to say. That's it. Have a great evening. Come back in the morning and we'll go deeper into it.